World Cup. Jesus, dramatic.
Hmm?
Can't
Okay,
you
I'm
count?
lost.
Count the Ballon d'Or, count the World Cup, trophies, count anything, count trophies, count goals, count everything.
I'm completely lost.
Lost in what exactly?
I don't know what you're saying.
Wait, repeat after me. Ni, repeat.
Me?
Ni, g,
No, no, don't do
Okay,
that.
yeah.
Don't do that. Don't do that.
repeat it.
Sorry,
No,
Ni,
no,
g.
no, 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 no,
Oh, my
no,
bad.
no. We're
It's
streaming.
Mr. Slave streaming.
Oh,
Like,
he's
we
live streaming. Oh, my bad.
can't do that.
Anyways, we could say it. Quantum spin? What is quantum spin?
That's what we're going to find out. We don't know. I don't know what that is.
SAYTU. Anyways.
La 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 la
Oh, I love hearing
la.
you singing. You're actually super, like, your voice is super good. You should be singing more.
Yes, yes.
We can't hear you, Mr. Slave.
Wait, you cannot
You're
hear
like too
me?
far away from the mic or something.
Wait,
Or
I'm
the
too
mic's too
far.
low.
Wait, let me see. One, two, three. I'm too late. I'm too late. I'm too late. One, two. No, I'm good. My mic is good. What do you mean?
My mic is good.
I think my mic is good. Wait, let me give you
And
No,
guys.
your mic is
Daniel's
super
volume.
low.
I'll
Daniel's
give
volume
you.
is
Super
like
low.
crazy.
Wait, my
Increase your
volume is
volume.
bad? My volume is
Yeah,
Yeah,
bad?
volume is kind of low.
What do you
Yeah.
mean? I'm listening
it's
to the
super.
stream. It sounds good on the stream.
Okay.
Name.
I don't know.
I wanna say the hard R so bad. Oh my
No,
god.
don't do that.
I wouldn't, yeah, I wouldn't. I wanna do it, but no, don't worry. So, Mr. Slave, could you check the side chat?
The side chat? But I'm
Yeah.
streaming, you know that, so don't do anything
Oh,
bizarre.
so no, don't worry. I'm sorry. Yeah, Agur. No, don't worry.
Wait, how is my audio? It should be fine.
No, it's super low. Like I have your audio at 200, so I can hear you.
Oh, let me check.
200.
No, it should be fine. I don't see an issue.
Yeah,
Oh,
I
One,
now it's
know.
better.
now it's
Yeah,
better? Wow.
super.
Yeah, but like it has a lot of echo, but it's better.
It's
Still
not
has
echo. It's like a noisy.
it's
It's like
noisy?
there's no any noise cancellation. Yeah, there's no any Yeah, but it's fine. It's
It's
fine.
fine.
Yeah.
Okay. Uh all right. Okay.
Now seems low again.
It's
Yeah.
low again. Let me check.
Yeah.
Wow.
Well,
It's on
now
100% now.
now it's high.
Yeah,
Yeah,
now
Yeah,
it's
but
low.
it
normal.
keeps every time I raise it, it drops. I raise
Yeah,
it
me
and it
too. Wait,
Weird.
drops.
just keep it. Just keep it.
I
Like
can't. I can't. It's doing whatever it wants. Let me try doing something. Wait, leave Discord. I gave you a link. Please join my link. La, la, la. No. Oh, okay. That's nice. Okay. Yeah, join me on StreamYard. It's easier.
a new video with Mr. Slave, our boy, our friend, our cousin, our father, our stepfather, and we are going to discuss about quantum spin, and Overmove versus gay. Actually, yeah.
Second, let me just tell my friend. 1 second. Anyway, let me add Cenas.
Wait, can you see the side chat?
No,
I'm
no.
not talking. I'm not
I,
talking in Discord. I'm talking in your in
yeah, I see it.
Streamyard.
Yeah. We'll get started with quantum spin. We'll start doing research on quantum spin. Let me just charge my other battery. Where's my other battery? It's gone. Where's the other battery?
Oh wow! Holy
That's
moly
one.
macaroni! Holy moly
Oh, the other battery is in the
macaroni!
other room. Okay.
Skibidi toilet.
Okay, let's get started. So Andrew, you have a definition for quantum spin. Can you explain to me quantum spin?
Sure, quantum spin. I have already told you the definition. Can you read it? Because you're native, so
I'll
people
put
can
it in the
understand it.
chat. I'll put it in the chat, and also let me put the link in the chat.
Sure.
Okay, so I'm going to leave Discord. Okay. All right. So your definition, what NG objects? What is that? Oh, spinning objects. Okay. So quantum spin is an intrinsic form of angular momentum carried by elementary particles independent of their motion. It determines magnetic properties and follows quantum rules, unlike classical spinning objects. Yeah, but that's, well, I don't know what that means. I don't know what intrinsic angular momentum, I don't know what that means. I'm looking for a mechanical definition of spin. Okay, let's look up on YouTube quantum spin. I was listening to stuff about it and I don't know what it is.
The quantum spin of fundamental particles such as electrons is profoundly different from the concept of spin in classical physics. In classical physics, the spin of an object can be described by an arrow pointing along the axis of rotation.
I think first we need to discuss the first time spin was discovered. Do you know how spin was discovered?
How it was discovered? I think that was Pauli.
Pauli? Wolfgang Pauli?
Yeah, I think that was the guy who first. At least he was the guy who first theorized it. Now I don't know about discovery for sure. Can't be too sure about that one.
Let's search how was quantum spin discovered? Was quantum spin discovered? Understanding spin. What is quant? Wait, let me get rid of this. Okay. It makes sense. What is quantum spin? How was it discovered? It's like what I noticed. I was thinking about this last night. There's no videos on YouTube of any modern physics experiments. Nothing about there's no videos of the double slit experiment. There's not a single video on YouTube. Not a single video on YouTube of the double slit experiment. Of course, there's no videos of quantum entanglement. There's no videos of spin. There's no videos. That means no one has reproduced these experiments.
I mean, double slit experiment. The Action Lab guy had one.
Hoyt Action Lab. What did he reproduce?
I think he had
He
one.
reproduced quantum spin.
No, double slit experiment. I think he had that.
The double slit experiment? No, he did not. No one reproduced the double slit experiment on YouTube.
I'll try to look for it.
You're not gonna find it.
Oh, Veritasium has a video once.
No, Veritasium never reproduced it. No one has ever reproduced it on YouTube. The double slit experiment reproduced. No one has ever even looked it up. YouTube doesn't even know how to autocomplete the double slit experiment reproduced. The real double slit experiment. Huygens optics. Yeah, he uses optics, and I don't even think he was successful at reproducing it. Let's see.
I'm finding some videos.
Okay, even if you find one video, that'd be nice.
Okay, wait a minute.
Experiment. And hello everybody. This video is about the double slit experiment. And maybe you wonder why somebody wants to make yet another video about a more than 200 years old experiment, especially with already tons of videos on YouTube regarding the subject. Well, for one, most videos don't show you the experiment, but just show you people talking about it. But in this video, we'll have a look at the real deal. And because I show you my own version of the experiment, there is a good chance that you will see aspects of it that you have never seen before. My version of the experiment uses slits that have a width in the order of only a few wavelengths of light, which is actually significantly narrower than used in most experiments. And we will study the fraction.
Wait, who's making noise?
Oh, that must be me clicking.
Under a microscope instead of at a large distance on a screen. Now, this allows us to look at a few aspects of the experiment with much greater detail. So to perform the experiment...
Yeah, but this is just the double slit experiment. This is not the one. I don't think he's shooting one particle at a time.
Oh, you want that one? That one?
This is just he's just proving that light.
Find that on YouTube.
He's just firing a laser beam through two slits, and he's showing that light is a wave. So that's useless.
Yeah, the other one I doubt you'll find that on YouTube.
So we need the electron. And he's the only one that reproduces any double slit experiment. But the electron double slit experiment, there's nothing. The electron double slit experiment, nothing. I mean, the only one who discusses the experiment is Feynman in this. I don't know how old this video is. It's very old, and this is the most detail I've ever gotten about the double slit experiment. You can barely understand what he's saying. The audio is so terrible. And this is after noise reduction. You can barely understand what he's saying.
Back here. If I knew enough about that electron, has internal wheels, internal gears, and so forth, that the fact and that this is what determines for which hole it goes.
You can barely understand what he's saying.
Yeah.
And this is the most information you can get about the double slit experiment. The most. And he doesn't explain what a detector is, just he explains properties of the detector. I don't even know if he ever saw the double slit experiment or a double slit experiment. I don't think he ever. I think he maybe read papers about it. She tried reproducing the double slit experiment, but again with light, not with electrons. So it's useless. and everybody else is just talking about it. This is just the reproduction of the output. He doesn't show the setup. Nothing. And there's no audio. Maybe there is.
Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the bibosom, thus creating a uniform distribution without any interference when accumulated. Under such condition do electrons...
Anyway, so we're going on almost zero information. So we are expected, we as theoretical physicists, that's what we are apparently. So we're expected to go literally on zero information. We're going on hearsay. All we have is hearsay. We don't even have first-hand hearsay. It's not even second-hand. It's third, fourth, 10th removed hearsay of rumors about an experiment. This is no way to do science. This is useless.
Yeah,
And that's
you're right.
what?
Unfortunately, you're right.
Right. So, and this is quantum physics. It's not just quantum physics. It's every physics today. If you want to be a citizen doing science, you can't. This is very similar to how religion was before the printing press. So before they invented the printing press, no one had a Bible. No one could read. You could only hear stories about the Bible from the priest. You couldn't read the Bible yourself. You didn't know what the Bible says. You had no access to the Bible. All you had access to is the priest, the reverend, whatever he told you, the Bible says, that's all you knew. And, you basically had access to it for a couple of minutes on Sundays. That's it. If the priest even discussed the Bible. Usually the priest didn't even discuss the Bible. He just brought it up. By the way, if ever. And that's what religion was like. And everyone believed this thing. But no one knew what they're believing. It was hearsay of hearsay of hearsay of hearsay. No one knew anything. And then they invented the printing press, and then everyone got a hold of the Bible, and then people started reading the Bible, and then whatever. Then people became basically atheists, very very quick in short succession after. So this is what's happening today with science. There's basically, I don't have any access to any experiment. Basically, I cannot conduct any experiment, and all I have to go on is hearsay. It's trust me, bro, we did this experiment, trust me. And I have almost zero information about these experiments. Certainly no video evidence. It's trust me, bro, and they don't even give you, when you read the original papers, they usually don't give you access. I don't think they ever give you access to the raw data. They just give you access to whatever they publish, which is not the raw data. It's just there. It's whatever they want to publish after they massaged it as much as they want. So this is the sad situation that we're in. So I don't even know what to trust. How can I just trust people like this guy? All he knows, he's a theoretical physicist. He's not an experimentalist. He's never done this experiment. I don't think he ever saw this experiment. So all he's discussing is hearsay. This is ludicrous. This is atrocious.
Yeah,
And
unfortunately.
all we have access to is animations. More animations and more and people discussing he never saw anything. He's just discussing the animations that he was shown whenever he studied this. So now this guy's an experimentalist, but I don't know if he experimented with the double slit experiment. He works at Fermilab. All they have is like a particle accelerator. Maybe he has access to this, but this is optics. This is not an electron, and this is probably stock footage. So I don't even think he has access. He doesn't conduct experiments. I don't think he conducts experiments. He works with the Tevatron, with the accelerometer at Fermilab. Maybe he just teaches there. I don't know. He says he's an experimentalist. And here is double slit performed, but only the output is shown. They don't show us the setup. No setup. If I want to reproduce the electron double slit experiment, I would know how to begin. There's no setup. I've never seen a setup explained. Here, do this. Go to the store, buy this, then buy that, then connect this, then that. Nothing. So this is very sad because I need to be able to run. I have so many ideas of experiments that I want to conduct for the electron double slit experiment. I want to test different slits, different distances between the slits. There's so much to test, different thickness, different materials, detectors. There's so many variables I want to play around with. That, we conducted, trust me, bro, we conducted this experiment. Here's the output. Now, based on that one experiment, for 100 years, people are trying to come up with theories. This is no way to do science.
Yeah, that's very strange. It's like scientists today don't make any experiments, basically. They make one experiment every 50 years.
Yeah.
And then they make theory, the rest.
Right. And then they also they all teach the same stuff. It's like they all repeat. They're all explaining the same things. They all agree with each other. It's like they all learned everything from the same place. They don't say, I conducted this experiment and I noticed. They never noticed anything. They never tell you what they noticed. Like if you listen to me, it's always what I noticed. It's always what I learned. It's always my theories. It's always me. I hardly ever bring up what I hear. It's like I'm trying to understand something, but usually I have to come up with a whole new philosophy. My philosophy of it's like my philosophy of science is completely different than theirs. They don't even, I never heard them explain their philosophy of science. It's like, yeah, I don't even think they know philosophy of science. They probably think, oh, you want to learn philosophy of science? Yeah, go study a course in the university, philosophy of science. They'll teach you what Popper said and what, what's his name said, what each and every one of them said. Yeah, they'll teach you all the different philosophers of science, but they wouldn't say, here's my philosophy of science. Like Professor Dave explains. What's his philosophy of science? I don't know. Does he ever conduct experiments? I don't think so.
Yeah, they just repeat information, basically. That's
right.
all.
And this guy this is Veritasium, carrying this box, proving to people the original double slit experiment. And all he's showing, in this entire video, he doesn't even show us. Like I don't even know I don't think he's showing anything to us. He's just showing people. He doesn't show us what's in the box. Maybe at one point he showed it for a split second, and I couldn't even understand what he's showing. He's showing people looking and, oh, they're so amazed. Oh, they're so, yeah. Okay, there it is here. This is what they're seeing. This is his double slit experiment. Behold.
Yeah.
Amazing. That's amazing. That's amazing. That light going through two slits spreads out like this. Wow. This proves light is a wave. Wow, we didn't know that. That's all that he proves. That's it. That's his double slit experiment. So he wastes all our time to show that light is a wave. Yo, wow, light is a wave. Wow, we could not have imagined that. So this is a big problem. This is not a small problem.
No, it's
A
definitely
real
not
life.
a problem. It's definitely not a small problem. That's for sure.
It's not a small problem. I think it's maybe the biggest problem. So I don't know. So we're going on no information. No, we don't have access to a lab. Very sad. So I don't know. I don't know what to do. Everything is animations. Whiteboard, blackboard, animations. Okay. So unfortunately, all we have to go on is secondhand information, third hand, fourth hand. Okay, let's see what they say. What is this spin? Okay, again. So what is quantum spin? Okay, this is the Science Asylum.
Hey crazies, let's talk a little more about quantum spin. I mentioned it briefly in this video, and some of you were still asking about it. The short version is that it's a little bit of angular momentum. But that always brings up a question. What is angular momentum? Which I can answer, but honestly, it's not going to help you. Electrons do not orbit. Electrons do not spin. We know not where they're going. We know not where they've been. Particles like electrons can't possibly be doing this. Remember in this video, I said the upper
Okay, so it's a major problem. We don't know.
limit on the size of the electron was 10 to the negative 18 meters, the smallest distance we've ever measured. Let's assume electrons are solid spheres, which isn't necessarily as far-fetched as it is for chickens or cows. If those electrons have a diameter of 10 to the negative 18 meters, to be spinning with an angular momentum of 1/2 h-bar, the outer edge would have to be moving at almost 1,000,000 times the speed of light.
So it would have to move at 1,000,000 times the speed of light. So let me get this straight. Well, just let me get this straight. So entanglement shows instantaneous communication across the universe. That's not a problem. But suddenly the speed of light is a problem. But from spin, they conclude entanglement, which is a violation of the speed of light. So here, no, it can't be spinning because it would be a violation of the speed of light. But the conclusion, entanglement, oh, that's definitely real. Yeah, and there's no contradiction.
They can violate locality. They can violate.
Yeah, I mean, they don't have the conclusion is
speed limit.
Right. The conclusion of quantum mechanics. Yeah, we can violate the speed of light. The speed of light is not only can we violate the speed of light times 1,000,000, we can violate the speed of light times infinity. There's instantaneous communication across the universe. But notice that when we want to analyze spin, oh, it can't be spinning because that would be a violation of the speed of light. So just tell me, which is it?
Well, nobody knows.
I mean, but the contradiction between this philosophy that we cannot violate the speed of light, and then the conclusion is entanglement, which is a complete violation of the speed of light, and they don't even mention the assumption. I don't know what to say to this.
And the smaller the electron is, the faster it would have to be spinning. The only possible conclusion? It's not spinning. Just think of it this way. Particles have all sorts of properties: mass, charge, position, energy, etc. Spin angular momentum, or just spin for short, is one of those properties. We can sort these properties into two categories: properties the particles have because of what they are, and properties they have because of what they're doing. Spin, as it turns out, falls into the first category.
Okay, that makes sense. Whatever spin is, it's intrinsic. From what I understand, it's like mass and charge, because an electron always has the same spin. Whatever that spin is, the amount is always the same. Like you cannot accelerate the spin of an electron to any value you want. Every electron comes with the same amount of spin, just like the same mass, the same charge. Okay, that makes sense. That I can agree with.
It's a type of angular momentum a particle has just because it's that particle. And
that doesn't make any sense. How can you tell me that the angular momentum is intrinsic?
Yeah, that's weird.
So, yeah, that's weird. So that's you cannot expect me to believe that, to believe something. I cannot believe what I cannot understand. And since I cannot understand it, there's no point in asking me to believe it. I can temporarily. So I came up with this notion that temporarily I can agree with it, with something. Temporarily. As long as Einstein said in the EPR paper, it's incomplete. If you want me to go with it temporarily, I can. As long as we agree that quantum mechanics is incomplete. But if you're going to tell me, no, that's complete, then I'll tell you no. Then I'm not going with you. Then we have to stop.
Yeah, basically.
And for no other reason. It shouldn't even be called spin. Intrinsic angular momentum would be more accurate, but it's not nearly as catchy. Intrinsic? Intrinsic? Tang? Ugh, the reality is just so unfamiliar, there isn't a better word for it. But how do we know it's there? Magnets. Any charge with any kind of momentum is going to have a magnetic field, which means it's going to be affected by another magnetic field. We'll stick with electrons for now because, well, they're easy. Experiment time! There was this experiment done in 1922 called the Stern-Gerlach experiment. Full disclosure, Otto Stern and Walter Gerlach did not use a beam of free electrons, because that ain't gonna work. Charge is a bigger influencer than spin, so they'll all veer off in the...
What do you mean that's not going to work? Why would that not work?
Yeah, that's a good question.
Like, if it has intrinsic spin, then that spin, why would it not work? I don't understand. Why does it have to be like silver, outer shell, whatever? Why? It's basically a neutral. It's a neutral atom. Silver atom is neutral. Okay.
Same direction if they get too close to a magnet. Charge, such an attention hog. Anyway, you need to make it neutral, like a whole atom. Stern and Gerlach used silver, 'cause reasons, but I don't want to get caught up in the details of the experiment. All that matters is we now have an atom that we're going to pretend is a massive neutral electron. I know, it sounds silly, but that's how I feel about all experiments. Theoretical physics is superior. Next, we need...
It says theoretical physics is superior.
Superior to what?
What?
Superior to what?
Superior to experimental physics. Like you heard what he said about experimental physics.
We're going to pretend is a massive neutral electron. I know, it sounds silly, but that's how I feel about all experiments.
He feels all experiments are silly.
Oh, that's why. That doesn't make sense.
There you go. I don't know. I don't know why he says that, but apparently he really believes it. I don't know why he says that.
I mean, he's probably being ironical.
No, I don't think so.
You
No.
really don't think so? Okay.
I mean,
I don't know what to say.
Because they don't want to be experimental. Like being an experimentalist is like being a garbage man.
Yeah, that's
Like,
weird.
it's-
I would like to be an experimentalist more. It sounds a lot more fun.
I don't know about fun. I just need. I cannot trust anyone. I cannot trust. I need to be able to reproduce an experiment. I don't care if I reproduce it. I just need to be able to reproduce it. And the fact that I'm not able to reproduce experiments at will, that's terrible. There should be labs that invite people, like they used to have public lectures, and in the public lectures, they used to demonstrate experiments. That's when you had gentleman's science. Like the scientists were funded. So only very wealthy people, it's usually lords and stuff like that, they used to be scientists. You couldn't be poor and be a scientist, and you could not have been a government employee and be a scientist. You could have had a patron, and he would have funded you. That could have happened, but it's still private. Anyway, they used to have public lectures, and in the public lectures, they used to demonstrate experiments. And people used to go to these public lectures and watch experiments. But today, when they have public lectures, it's never experimental. It's always theoretical. It's always with a PowerPoint presentation.
Theoretical physics is superior.
Terrible.
Next, we need something to control that electron. Say, I don't know, 2 strong magnetic poles shaped like this. Again, don't get caught up in the details. Think of it as just a spin separator. If we send a bunch of these caught up in the details. Think of it.
Wait, this is north-south? What?
What details is he talking about?
I don't understand. What?
What details is he talking about? Like, he's not
I don't
talking
know.
about any details. It's like,
I don't-
that could have been a
Yeah.
detail of not talking about anything.
But this magnet, notice that it's north-south. I don't understand this magnet. What is... So it's 2 magnets, north-south and south-north?
Yeah, but I don't know why they're symmetrical. Oh, okay. So
2 strong magnetic poles shaped like
This is north-south.
this. Again, don't get caught up in the details. Think of it as just a spin separator. If we send a bunch of these electrons through, we get 2 distinct groups, which we call spin up and spin down. Since the biggest possibility is plus 1/2, we call these spin 1/2 particles. But there's nothing special about up and down. We get 2 groups no matter how we orient this thing. Each of the 2 major directions can only have 2 possible values, plus 1/2 and minus 1/2.
Einstein hated this experiment.
It is? I ate this experiment as well.
I mean,
100%.
no, because you know what I heard today? That Bohr said we should stop talking about conservation of momentum. He said
Why?
conservation. He said many crazy things, especially in response to the EPR paper. His defense against the EPR paper was completely ludicrous. But one of the things he said is we should stop respecting conservation of momentum. Anyway.
It sounds so random.
No, he was, I mean, because that is where quantum mechanics, an incomplete quantum mechanics, this is where it leads you. It leads you to becoming anti-scientific. That's, and that's why you have all these woo-woo thought leaders, whatever, that they always base themselves on quantum mechanics. All the nonsense comes out of quantum mechanics. They allow themselves to say anything, just anything and everything. Well, quantum mechanics showed us that, and then fill in the blank. You can say whatever you want. Once you say quantum mechanics showed us, you can say whatever you want.
Never 0. I wonder what that looks like. If all the directions are plus 1/2, the spin arrow looks like this. But But this is quantum mechanics. Only one of those directions can be definite at any one time. What I mean is, if one of the directions is, say, definitely 1/2, like for sure, then the other two directions are in some weird combination of both plus 1/2 and minus 1/2. It's called a quantum superposition.
Wait, why would he say that? I don't understand. If one direction is definitely plus 1/2, then the other ones have to be in a superposition of plus and minus 1/2? Why?
I mean, it's
I
according
don't-
to the theory.
But why? I mean, he says it should be. Why should it be? I don't understand.
So spin up actually looks more like this. There are only 4 possible directions.
What is this? I don't even know. What is he showing? What is this? I don't understand anything he's showing. He's not explaining anything.
For that arrow, all pointed up. If we then try to measure left and right, we might find that it's pointed right, except now it's in this state. We don't know if it's up or down anymore.
What is he showing? What are these 4 arrows? I don't understand. Okay, this is useless.
Supposedly like the quantization of spin.
I don't understand. I honestly don't understand. Okay, this guy I listened to.
Spin is a bit of historical. So what happens is that this electron, like every electron, has a charge, but it also has a magnetic dipole. It's like a tiny, tiny, tiny magnet. It's called a spin. The word spin is a bit of historical misfortune. So to some degree, in a classical world, you can think of a electrically charged particle, so something that has a negative charge. And if you make it spin, literally spin like a gyroscope around an axis, it will in fact produce a magnetic field. Okay? So it will be like this magnetic dipole. And so you can describe this object as a magnetic dipole that points in some direction.
I don't understand. How is it spinning? In which direction is it spinning?
Is a purely quantum mechanical property that actually comes from solving some relativistic equations of quantum mechanics, the Dirac equation. And the most striking example to explain why you cannot think of the spin as actually the electron spinning on itself is when you think of the neutron. The neutron also has a spin, but it has no charge. So how can you say, oh, the neutron is spinning on itself, therefore it produces a magnetic dipole? Well, the neutron has no charge, and yet it has a spin, just like the electron and the proton. So imagine a solenoid where you have wire.
So how do you get this field that he's showing? How is it spinning? Which direction is it spinning? I don't understand. Spinning like a coin? Yeah, I think it's spinning like a coin on a table. Okay, whatever.
So on this side you have current going in, and on this side you have current coming out. So you have the current going this way. That produces a big magnetic field in this.
What? What is he? I don't understand. What? So his lines make no sense. So it's going into the board on the right and it's coming out of the board on the left. So which way is it spinning? I don't understand. Oh my God, this is terrible. So unclear. Oh, look, we came up. We're showing up on the search.
No, not bad.
Yeah. Okay, Dirac's belt trick, topology, spin 1/2.
To perform the Dirac belt trick, you'll need 2 things. 1, a belt. And 2, a large book. The book is to keep one end of the belt in place while the other moves around. To begin, take the free end of the belt and turn it by 360 degrees. You will now see a twist in the belt. The goal is to find a way to take out this twist. What makes this interesting is that you're not allowed to rotate either end of the belt, so you can't just directly undo the twist. However, you are allowed to move both ends around in space, as long as you don't turn them while doing so. Now, you have to try this for yourself to be convinced, but no matter what you do, you won't be able to undo the twist in the belt. So that was a big failure. However, in the beginning, instead of twisting the belt by 360 degrees, what if we instead twisted it by 720 degrees, which is 2 full rotations? Can we undo the twist now? Well, watch this. Amazing. We can't undo a 360-degree twist, but we can undo a 720-degree twist. That's the Dirac belt trick. Paul Dirac, one of the greatest physicists of all time, invented this trick in order to help explain to his students the bizarre nature of quantum spin 1/2 particles, such as electrons and protons. An older version of this trick was popularized in the book Riddles of the Sphinx and Other Mathematical Puzzle Tales by Martin Gardner. For this older trick, the first step is to put your belt back on. Then get a pair of scissors and 2 pieces of string about 10 feet long. Thread the strings through the holes in the scissors and tie off the ends in 2 loops. Now, step on the 2 loops of string and hold the scissors right in front of you, straight up. Then, rotate the scissors around by 720 degrees. Once again, you can take out the twist in the strings by moving the pair of scissors without rotating them. But this is sort of dumb, so let's just stick with the belt. Anyway, what does any of this have to do with quantum mechanics? Well, if you take a normal object, like the soup can, and rotate it 360 degrees, it'll end up exactly how it started. But now let's say you have an electron. We'll paint a little plus sign on it so we can see how it's oriented. Let's see what happens when we rotate this electron by 360.
Why is the electron? Oh, plus sign is not because it's negative. Okay.
Degrees.
I mean, it's not positive. It's just the plus sign is just to see it rotating.
What? What happened to the plus sign? All I see is a stupid minus sign. Well, let's keep rotating it and see if that helps. Ah, look, it's a plus sign again. So we can see that when we rotate an electron by 360 degrees, it doesn't return to its original state, but rather a negated version of its original state. However, when we rotate it by
What?
120 degrees, then we get back the original state. This is the property of the electron that the Dirac belt trick attempts to explain. Now at this point, you may be saying, wait, a 360-degree rotation is a 360-degree rotation. You can't say it's only a half. Well, in order to explain this trick more precisely, I'm going to have to introduce some concepts from the branches of mathematics known as group theory and topology, which will take some time. Having said that, I think it's well worth the effort, because the story of the Dirac belt trick is, in my opinion, one of the most wonderful and fundamental in all of physics. Imagine you wanted to rotate this snowman. You would have to specify 2 things. 1, an axis of rotation, and 2, an angle of rotation. Now, we could rotate any object we want, and admittedly, the snowman is a little silly. So let's instead use these coordinate axes. We can once again choose an axis and an angle to rotate it by. Throughout this video, whenever I rotate these coordinate axes, I'll always include a ghostly image of its original orientation. Now, from here on out, let's always measure angles using radians instead of degrees. So for instance, pi over 2 radians is 90 degrees, pi radians is 180 degrees, 2 pi radians is 360 degrees, and 4 pi radians is 720 degrees. Anyway, to recap, you can specify a rotation with 2 pieces of information. 1, an axis, and 2, an angle. We'll define the rotation to always go in the counterclockwise direction around the axis, in accordance with the standard right-hand rule, which says that if you point your thumb in the direction of the axis, then you rotate in the same direction that your fingers are curling. Now, let's package these 2 pieces of information together in a different way. Instead of using an axis and an angle, let's use a single vector, which points in the direction of the axis, but has the length of the angle theta measured in radians. So, using this, how can we understand what the space of all rotations is? Abstractly, the space of rotations is a set, and individual points contained in the set each correspond to 1 rotation. Concretely, we can picture the space of rotations as follows. Here we have a 3-dimensional ball with a radius of pi. Now consider a point contained in this ball. This point corresponds to a rotation, namely the one given by the vector, which has its base at the center of the ball and its tip on the point itself. This vector will have a length ranging from 0 to pi because the ball itself has a radius of pi. Remember, the direction of this vector corresponds to the axis of rotation and its length corresponds to the angle of rotation. To let you soak this in, I'm going to show the vector in the space of rotations on the right and the rotation it corresponds to on the left. Now, there's actually something kind of funny about the space of rotations. Notice that if you rotate around an axis by exactly pi radians in the clockwise direction, the result is exactly the same as if you had rotated by pi radians in the counterclockwise direction. Therefore, this means that a point on the boundary of our ball corresponds to the exact same rotation as the antipodal point on the other side of the boundary. So, we can have a point in the space of rotations go out to the boundary and come back out the other side. While it looks like the point has jumped discontinuously, this is actually just an artifact of our visualization. So it's actually not quite correct to say that the space of rotations is a ball of radius pi. We also have to include this extra stipulation, which says that antipodal points on the boundary of this ball are equivalent to each other. Let's now give a summary of part 1. It takes 2...
I didn't get that. What? Are you following?
Yeah.
Let me see.
pi radians in the
Explaining rotations.
Yeah, let me see.
clockwise direction. The result is exactly the same as if you had rotated by pi radians in the counterclockwise direction. Therefore, this means that a point on the boundary of our ball corresponds to the exact same rotation as the antipodal point on the other side of the boundary. So, we can have a point in the space of rotations go out to the boundary and come back out the other side. While it looks like the point has jumped discontinuously, this is actually just an artifact of our visualization. So, it's actually not quite correct to say that the space of rotations is a ball of radius pi. We also have to include this extra stipulation, which says that antipodal points on the boundary of this ball are equivalent to each other.
Wait a minute, let me see.
Notice that if you rotate around an axis by exactly pi radians in the clockwise direction, the result is exactly the same as if you had rotated by pi radians in the counterclockwise direction. Direction.
Okay, but it's only true for, it's a special case. Just when you do pi radians, which is, pi radians is 180 degrees.
Yeah.
So when you do pi radians, just happens to be that pi radians are invariant to the direction.
Rotated by pi radians in the counterclockwise direction. Therefore, this means that a point on the boundary of our ball corresponds to the exact same rotation as the antipodal point on the other side of the boundary.
Only for pi radians. So why is he generalizing it?
So we can have a point in the space of rotations go out to the boundary and come back out the other side. While it looks like the point has jumped discontinuously, this is actually just an artifact of our visualization. So it's actually not quite correct to say that the space of rotations is a ball of radius pi. We also have to include this extra stipulation, which says that antipodal points on the boundary of this ball are equivalent to each other. Let's now give a summary of part 1. It takes 2 pieces of information to specify a rotation, an axis and an angle. Alternatively, we can use a vector, which points in the direction of the axis and has the length of the angle. We can visualize the space of rotations as a ball of radius pi, where each point in the ball is one rotation. We must identify antipodal points on the boundary of the ball, because clockwise and counterclockwise rotations around an axis by 180 degrees are really the same.
Maybe it's not only for pi radians. Maybe it's like the completion. You go. Like I'm trying to visualize the point and the anti-point. So a point and an anti, like if you go in the positive x or in the negative x, the one complete gives you the same result. So if you go pi in this direction and pi in the other direction, they're symmetric. But if you go half pi in one direction, or
Or what?
If you go a little bit, yeah, I think I understand why he generalized. He's not explaining it well. He's skipping it. He's giving an example of pi, but he should have given an example of half pi as well.
Therefore, this means that a point on the
See, this point is equivalent to
boundary of our ball corresponds to the exact same rotation
that point. That's one extreme case.
as the antipodal point on the other side of the boundary. So we can have a point in the space
But it's true for any
rotations
point.
go out to the boundary and come back out the other side. While it looks like the point has jumped discontinuously, this is actually just an artifact of our visualization.
It's the same point. So you can continue from that point on, you can continue. So you can move forward until here. When you get to here, it's the same as here. Then the next thing he's saying, well, if it's the same, then we can continue here. So it's continuous. Basically, we can continue by jumping, by hyper jumping, by doing a hyper jump. That's basically where the word hyperlink came from. So you get to here, and then you're saying, oh, this is the same as this. So if I can skip to here, I haven't changed anything, and now we can just continue.
Continue.
In the same direction. So you can continuously rotate if you want to continuously rotate in the x, let's say the red is the x direction. You want to continuously rotate in the x direction. So you move forward, you move to the positive x in the x direction. You get to here. Now you skip back to here, and then you continue moving in the positive x direction, and it's completely continuous. You're always continuously moving in the positive x direction. He didn't explain it. It's fine.
That's weird.
So
It's fine. It's just an artifact.
It's actually not quite correct to say that the space of rotations is a ball of radius pi. We also have to include this extra stipulation, which says that antipodal points on the boundary of this ball are equivalent to each other. Let's now give a summary of part 1. It takes 2 pieces of information to specify a rotation, an axis and an angle. Alternatively, we can use a vector, which points in the direction of the axis and has the length of the angle. We can visualize the space of rotations as a ball.
Let me just ask my friend. Maybe he wants to go out tonight. I don't know. Oh, it's too late already. Oh, it's too late. It's far too late for goodbyes. Just check. Forget it. I need to text her something that I need to be able to continue tomorrow because I just dropped off the earth. Forget it. It's impossible. I'll just text her tomorrow. Okay, let's continue.
Ball of radius pi, where each point in the ball is one rotation. We must identify antipodal points on the boundary of the ball because clockwise and counterclockwise rotations around an axis by 180 degrees are really the same. Now that we understand the space of rotations, let's think about paths through the space of rotations. Here's an example of a path.
Wow, incredible. So you need to know all of this in order to understand spin? I mean, if at the end of this we'll understand spin, fine.
Okay.
I'll swallow whatever shite I need to swallow in order to understand spin because I really want to understand it. I'm really curious what spin really is. Why they called it 1/2?
It's sort of like a monorail with a point going around it in one direction. Here, I displayed the point going around the path alongside the rotation it corresponds to. Enter the belt. If you think about it, a belt is a lot like a path because it has a start point and an end point. As we'll see, it turns out that a belt does indeed correspond to a path through the space of rotations. Here's how. Choose a point along the belt. Now have the x-axis point along the length of the belt, the y-axis point perpendicular to the belt, and the z-axis point along the width of the belt. Now, as we move down the belt, our axes will change accordingly. Because every orientation of these axes corresponds to a rotation, we can see that the belt really does trace out a path in the space of rotations. Let's look at some concrete examples. Here's a path that rotates around the x-axis by an ever-increasing angle.
Yeah.
Now let's
So that's what we discussed before, that as long as you move along the x-axis, you finish on the right, you jump to the left, and you continuously move in the positive x, it's a continuous rotation. It's fine.
do the same thing around the y-axis. And here's a version around the z-axis. Here's a more arbitrary shaped path. This looks kind of messed up though. Okay, this one is important. This is the trivial path, the path that just stays right at the center of the ball. Note that the belt corresponding to the trivial path is completely straight. Okay, now let's talk about the belt trick again. Remember what I said the rules of the belt trick are? What makes this interesting is that you're not allowed to rotate either end of the belt, so you can't just directly undo the twist. However, you are allowed to move both ends around in space, as long as you don't turn them while doing so. What does it mean that you can't rotate the ends of the belt? Well, let's look at this path. Notice that it starts and ends at the middle. That means that the axes start and end completely unrotated. But let's look at what happens when we change the endpoint of the path. Notice that if the path doesn't end at the same place it starts, then the final configuration of the axes won't be unrotated. Therefore, our stipulation that you can't rotate the end of the belt means that our path in rotation space must end at the same place that it begins. Now, what was the goal of the belt trick? The goal is to find a way to take out this twist. Remember that a perfectly straight belt with no twist in it corresponds to the trivial path. That means that making the belt straight corresponds to contracting the entire path down to a point. Now, for the path we have here, that's very easy to do. However, let's look at the belt with a 2pi twist in it. Remember, this was the path we weren't able to undo at the beginning. And indeed, no matter how hard you try, you won't be able to contract this path. Intuitively, this is because the 2 points on the boundary are actually the same point. But if we wanted to contract this path, we'd somehow have to bring these 2 points next to each other. But we can't do that because they always have to remain antipodal. Now, what about the path with a 4pi twist in it? Let's separate out the 2 strands of this path a little, just so we can get a better look at it. Now remember, earlier I was able to get the twist out of this belt. So let's see what that looks like here. I know that was a lot to take in, so let's look over this a bit slower. Here is the path corresponding to a 4pi twist. Here, I've labeled the 2 pairs of antipodal points. For instance, the 2 points labeled A are really just 2 manifestations of the same point. Now, let's watch how this path can be contracted. Did you see that? Let's look at it again. Notice how the points A and B are approaching each other, which allows one part of the path to be pulled through the boundary and come out the other side. Pretty neat, right? Here's another way to understand how this path can be contracted. This time, I've kept the path straight instead of curved and colored the 2 different branches slightly different shades of gray. Let's see how these paths through the space of rotations act on our snowman at different stages of the contraction. Notice that there are essentially 2 rotations going on, which I've labeled 1 and 2. The contraction works by making the axes go from being parallel to anti-parallel, and then decreasing their respective angles of rotation. So let's give a summary of part 2. Each configuration of the belt corresponds to a path through the space of rotations. The trivial path.
All right. Do you understand anything?
Each configuration of the belt. I mean, it's just explaining rotations. Like, okay.
Did you study this?
No. But like it's just been talking about rotations. Like there's nothing really amazing to understand here.
Okay.
Corresponds to a perfectly straight belt.
I don't know why.
Some paths can be contracted to a single point without having to move their start point or their end point. The Dirac belt trick is a demonstration of the fact that the path corresponding to a 2pi twist can't be contracted to the trivial path, while the path corresponding to a 4pi twist can. Allow me to introduce some notation. This expression should be read as G is an element of G. That is, the lowercase g is one element of the set named uppercase G. With that out of the way, let's talk about groups. The word group in mathematics has a very specific meaning. Namely, a group is a set with an operation. More specifically, there are 4 rules that this operation must satisfy. The first rule is that if G1 and G2 are elements of the set G, then G1 plus G2 must also be an element of the set G. Here, we're denoting our operation with the plus symbol. We could have used a number of other symbols, but let's stick with this. The second rule is that there must be some element of the group, which we call id, which is short for identity, such that for any other element of the group G, G plus id is equal to G. The third rule is that if you add G1 and G2 together and then add it to G3, the result will be the same as if you added G1 to the sum of G2 and G3. The fourth rule is that for any element G, there must be some other element, which we'll call negative G, such that G plus negative G is equal to the identity. Here, negative G is called the inverse of G. These 4 rules are the exact rigorous definition for what mathematicians call a group. Now, this is all a bit abstract. Are the exact rigorous...
So the first one is, okay, a group G is a set with an operation. Do you know group theory?
Yeah, more or less. But it's just, you know what a set is?
Set is, yeah, that's just a collection. But a group, apparently, it has an... So a group is set with an operation.
Yeah, pretty much.
So if G1 belongs to a group and G2 belongs to the same group, then G1 plus G2 also belong to the group.
Very straightforward.
But that's the plus operation. He said we can do any operation, whatever the plus means. But that's the definition of a group, and that's the definition of the operation. There must be an element. So then a group is defined that there must be an identity that belongs to the group, such that for any G that belongs to capital G, G plus the identity element is still G. All right, like 0. Then associativity, that's fine. And then the negation. Okay. All right. So that's the definition of a group. All right. Remind me to kill myself after this.
First definition for what mathematicians call a group. Now, this is all a bit abstract. What's an example of a group? Well, one example is the set of rotations. Take, for instance, the rotation around the x-axis by pi and the rotation around the y-axis by pi. How do we add these together? Well, for rotations, plus just means that we do the first rotation first and the second rotation second. So to add these together, first let's rotate around the x-axis by pi, and then let's rotate around the y-axis by pi. Now, notice that this final rotation is exactly the same as if we just rotated around the z-axis by pi. So hopefully you can see how you can add two rotations together and get a third one. What about the identity element? Which rotation corresponds to?
Okay, that's pretty incredible. That rotation by x plus rotation by y is equal to rotation by z. That's amazing. So that makes rotation a group?
Well, that'll just be the trivial rotation, the rotation where you don't do anything. What about inverses? How do we invert a rotation? Well, if a rotation involves rotating around some axis in the counterclockwise direction, then we can undo it just by rotating in the clockwise direction. So we can see that every rotation does indeed have an inverse.
That's pretty amazing.
So that wraps up the explanation for how rotations form a mathematical group. This is a good opportunity for me to talk about matrices. Let's write the actual mathematical formula for the rotation around the x-axis by an angle of theta. We express the rotation as a transformation on a position vector. We can also write this as a 3x3 matrix acting on the original vector. To explain what distinguishes rotation matrices from any old arbitrary matrix, we have to discuss the inner product. Say you have two three-dimensional vectors r1 and r2. The inner product of r1 with r2, which can also be written as r1 transpose times r2, is equal to the sum of the products of their components. Geometrically, the inner product of two vectors is just the product of the lengths of the vectors times the cosine of the angle between them. Now, notice that rotations preserve both lengths and relative angles. This means that if you rotate both vectors together, their inner product won't change. In other words, if we denote the rotation matrix with the letter uppercase R, then the inner product of uppercase R times R1 and uppercase R times R2 is equal to the inner product of R1 with R2. For this equation to hold for any choice of position vectors, we need for the transpose of the rotation matrix times itself.
Do you understand any of this?
Okay, I wasn't paying much attention now. But yeah, I mean, it's now explaining. Okay, it's now explaining like how matrices can represent rotations, and how the inner product of vectors can depend on the rotation. But I mean, it's not nothing special, just mathematics.
Just together, their inner product won't change. In other words, if we denote the rotation matrix with the letter uppercase R.
Okay, the rotation matrix.
Yeah, it's rotation times the vector.
What is the rotation matrix?
A rotation matrix is like is like something you can apply to a vector to rotate it. Like you can multiply a matrix by a vector to rotate it.
So he showed it before.
Yeah. Okay. Yeah.
Form a mathematical group.
Like
this is a good opportunity for me to talk about matrices.
The signs of the angle.
Let's write the actual mathematical formula for the rotation around the x-axis by an angle of theta.
Okay, so that's the rotation of a vector xyz by theta. So x times x is x squared, x times, and then y times cosine minus sine, and then z times. Okay, so you get something.
We express the rotation as a transformation on a position vector. We can also write this as a 3x3 matrix acting on the original vector.
Oh my god, this is too much. I need to remember so much from such a long time ago that it's basically it's too painful.
Don't worry, it's nothing special.
Yeah, but he's not gonna.
See how the rotation matrix is like. It's whatever.
He's saying you can have. So this is matrix which represents the rotation. Okay, that's actually simpler. So it's the same. I see.
That's
Okay,
rotation around x, right?
So 1 times x
is invariant in that
and
way.
then and then cosine
Just the x is invariant in there.
theta y minus sine theta z. And y, okay, this is a rotation about angle theta around the x-axis.
Around x, yes, of angle theta.
How do you know? How can you tell that it's a rotation
Yeah,
about
because
it?
the x is invariant, as you can see.
Oh, okay, so x is not the x is the same. It's 1 times x
Yeah.
and then 0. So that's just x. So x is the same, but y and z are changing to something that has to do with theta. So x is the same, whatever the vector x was, but y and z are rotated as a function of theta. Okay.
To explain what distinguishes rotation matrices from any old arbitrary matrix, we have to discuss the inner product. Say you have two three-dimensional vectors R1 and R2. The inner product of R1 with R2, which can also be written as R1 transpose times R2, is equal to the sum of the products of their components.
Okay, this is too much. It's killing me. There's too much information, and there's not enough payoff. Just not enough payoff. I don't know where he's going with this, so I'm gonna forget about it. Okay.
I mean, he's explaining like everything about rotations. That's too much.
Yeah, it's too much. Let's see the looking glass. Okay. Oh, wait.
This. What is it? In this video, what is spin? It's something that apparently some particles have that you can measure, but what is it? In this video, I'll explain how we know spin exists, but also why we don't understand it. Spin was a latecomer to the quantum mechanics party. Even after Schrödinger wrote his famous equation and everything seemed to be working, people didn't realize it existed. Then people realized that some particles seem to have odd magnetic properties the original quantum mechanics didn't predict, and the source of that was labeled spin. To understand this, we're going to need one piece of classical electromagnetism theory. Whenever a charged particle moves, it creates a magnetic field. This is pretty amazing, and you can see it for yourself by putting the compass next to a charge-carrying wire. In fact, if you have a charged particle going in a small loop, this not only creates a magnetic field, that field pretty much looks like it's from a bar magnet. So then we expect charged particles moving around in circles to act as little magnets. Since that's something we know from classical physics, it was built into quantum mechanics too from the start. But eventually some experiments showed that there must be some other source of magnetism. I'm going to explain one of those, a simplified version of the Stern-Gerlach experiment. Let's say we have a bunch of electrons by themselves. They are charged, but they're not doing little loops, so they shouldn't be magnets. We test this out by putting them in a Stern-Gerlach apparatus. I'm not going to explain how the machine works, but what it does is this. If a small magnet is placed inside, it measures its orientation. If the magnet's north pole is up, it exerts an upward force on the magnet. If the magnet is the other way around, it exerts a downward force. Of course, there are other orientations. If the magnet is like this, the magnet is still somewhat pointing up, so the force is still up, but smaller. It's proportional to how much this magnet is pointing in the up direction. Similarly for this magnet pointing down. Say a magnet is on its side, then it has no force at all. But these aren't the only ways the magnet can be oriented either. It could be forward or backward or left or right or any combination. And so what happens there? Well, this machine only measures how much the magnet is up or down. If the magnet is like this, it's still pointing a bit upward. On the other hand, if the magnet was just pointing left or right or forward or backward, it wouldn't feel any force, and so it would go straight. So what we expect is if we shot through a bunch of magnets in random orientations, they all land between here and here and in a pretty smooth distribution. Of course, if we threw in a non-magnet, it wouldn't feel anything and just go through. So that's what we should expect with electrons. But we do the experiment and find something really odd. The electrons do experience forces as if they're magnets, but they don't spread out smoothly either. Half of them go up to the same height, and the other half go down, again, to the same height. Let's look at this second mystery first. If electrons really are magnets, we expect them to be randomly oriented, but these results would be like saying that, for some reason, half of them were pointing exactly up, and the other half exactly down. Well, maybe we did something very wrong when we prepared them that meant this happened. So to test that, let's do something clever. Let's turn the Stern-Gerlach machine on its side. What that does is, now the machine is measuring how much a magnet is pointing to the left or right instead of up or down. The more the magnet is pointing to the left, the more left it goes. If a magnet isn't pointing either left or right, it just goes through. Now let's use the same source of electrons we had before. We think that they're all pointing up or down, and so they should just go through this machine and they shouldn't be deflected at all. What happens? Half of them go right and half of them go left. So then they were actually oriented left and right all along, but that can't be right either. Let me explain how to think of this in the framework we built up in the last couple of videos. I can measure the up or downness of a particle, so that isn't observable. What are its eigenstates? Well, this experiment showed that the particle can only be fully up or fully down and nothing in between. So they are the only two eigenstates. We'll call them spin up and spin down. Now we can apply the quantum mechanical principle that to fully describe the wave function of this particle, we only need to describe it in one basis. So I can fully write the state of this particle in terms of up and down. This is weird because in classical physics, it wouldn't be enough to tell you the state of the magnet. I can't just tell you how much it's pointing up or down. I need to also tell you how left or right it is and how forward or backward. But in quantum mechanics, this is enough. Let's see what happens when we do some arbitrary combination. Here, since the square of this number is bigger, it has a bigger chance of being spin down, but it can still be spin up. It doesn't go 3/4 of the way down ever though. It's only ever up or down. But what about if I flip the machine on its side to measure the left-rightness? In quantum mechanics, if you tell me the wave function in terms of up and down, I should be able to figure out what the wave function is in terms of left and right. To be able to do that, we just need to know how.
Oh my god, this is so painful. I don't know what to do with this. I don't know what to do with this. Pain is too great. What do you think?
I mean, I think they're making a confusion between how the electron appears when it's measured, when it's subjected to an electrical field or a magnetic field, and how the electron actually is before it's measured. I think that's the entire problem. I really don't think there's anything more to it.
What?
I think they're confusing how the electron is before it's measured with how the electron is after it's measured.
What do you mean?
Yeah, because when you
You-
measure an electron, you make it interact with an electric field or a magnetic field, so it changes. I think they're just not addressing that.
Mm-hmm. Can you explain the Stern-Gerlach experiment?
Well, I have my view on it. I think the electrons change spin very fast when they interact with just about anything.
What is spin?
Spin. Okay, I mean, in a wave, spin is easy to conceptualize because it's just it like if you have a transverse wave, like things in the medium need to be spinning in a certain way to create a transverse wave.
Oh my god.
Like,
But
like
you have silver. Okay, the Stern-Gerlach is you have a silver atom. Silver atom, they say, it has one electron in the outer shell.
okay.
And
What
it
difference
is
does it
this, and they say this electron. That's what's behaving. That's causing the entire behavior. That one electron. That's what's special about silver.
Okay, so they shot silver atoms, right?
They didn't really shoot silver atoms. You don't shoot. It's just they burn silver, whatever, and then I don't know how they accelerated them. I don't even know if they accelerated them.
It's using a magnetic field.
Yeah, but there's no magnetic. It's not. I don't know. Okay, whatever. Somehow they shot silver. Okay. They moved silver through this field. Some go up, some go down. Why?
Some go up, some go down. Well, they align with the field, and then they are attracted by it, by the magnets. Like, what's the big deal?
The question is, why did they use it with silver? Why not use an electron? Like an electron, why should not? Because when they use an electron,
That's a good question, because probably if you shoot electrons, they just get attracted by the magnets.
that's what we know. That's how they discovered electrons are particles. They said, let's use a magnet, and it got deflected. They all were deflected exactly the same way. Why are electrons all deflected the same way if electrons have spin? If they have random direction spin,
Because they align their spin. Like the spin has to align. Like you know. Okay, maybe this is okay. So the idea of spin.
What do you mean align?
You can conceptualize a magnet as having a certain spin. Right, like for example, if you have a current loop, you will get a magnetic field that's perpendicular to the loop, right? So you can think that the spin is the current loop.
Wait a minute, didn't Einstein say that magnetism is just an artifact of electricity, because of the fast motion? The fast motion.
Did Einstein say that?
Yeah. He
I
said
didn't know.
he showed magnetism is just an artifact of electricity. That was his whole thing. I mean, that is an incredible
And but
explanation.
electricity and magnetism. Okay, so electric field and the magnetic field are complementary.
There's no such thing as a magnetic field.
Well, that is
Magnetism does not exist. It's all electric. Magnetism is what electricity looks like because of relativity. Relativity makes electricity look like magnetism. It's just because of relativity. That's why it needs to move. So if this is true, if we assume this is true, then the electron looks like a magnet because of relativistic effects. It's not really, there is no such thing as a magnet. It's because the electron is spinning. This spin creates, it's a magnetic lookalike, but it's really electricity. It's a moving charge. But they're not talking about that. They're saying, oh, it's a magnetic bar. But a magnetic bar internally, Einstein would say, is just a relativistic charge. Why are they not mentioning that?
But how is it just a relativistic charge?
That's what Einstein said.
Yeah, but I don't understand what he said.
What?
I don't understand why he said that.
No, he proved it. You can show it. Here, let me show you. But I need to kill myself. Let me go get some gum. My brain is shutting down. Every time I work on this, my brain shuts down until I figure it out, and then I wake up. But until I figure it out, my brain keeps shutting down. Give me a minute. I'll go get some gum. You know, I discovered really interesting videos from Japan of cute girls riding big motorcycles. It's so funny.
Well, Japan certainly has a lot of that. Japan, 100%.
Okay, Einstein, magnet, electric, relativity, whatever. We'll come back to this. Let's listen to the news.
The news? No, let's not listen to that guy.
This one.
It's more pleasant.
They're gonna They don't like it when I have music in the video.
All right.
Um,
This video shows a series of simulations involving a small particle. We'll start using the assumptions of classical physics. First, we'll describe the initial setup and then play the simulation. For simplicity, we'll assume a one-dimensional space, so the particle can only move horizontally along this line, either left or right. Here's our particle. It's starting at position 0 and has an initial velocity of 4 units per second. Now we'll play the simulation. Since our particle floats in empty space, it maintains a constant velocity. Note that time is slowed down by a factor of 2. We'll play all simulations this way. Here's how quantum physics describes the same thing. The particle is represented by a wave function, such as this one. It contains information both about the particle's position and its velocity, but it will take us a while to explain how to read it all. First, we'll explain how to read information about position. The wave function is rotating around the main axis, and its distance from it varies. Here, for example, the distance is high. Here it is lower. And here, even lower still. The particle is more likely to be found at a position where the distance is high, so it's more likely to be found here. Less likely to be found here. And even less so here. To better see the varying distances, let's draw a circle that touches the wave. Its radius shows us the distance at a given point. We'll slide it along the main axis and wrap the function with the resulting surface.
Very nice.
So we don't know exactly where the particle is, but we do know the probability distribution of its position. The wave function evolves with time according to an equation called the Schrödinger equation. This particular wave shape evolves by gliding to the right. In fact,
But all that happens is, at the end, we measure. The act of measuring forces the measurement to have a location. It's just a measurement. The particle is always a wave. It never the particle never collapses. The measurement, whatever the measurement is, it has a location. But the particle never collapses. The particle is always a wave. It never changes its mind.
it's moving at 4 units per second, but we'll explain about velocity later. Let's watch it again. Note how the wave is gradually spreading.
Let me check.
We'll explain this too later on. The particle is too small to be observed directly, but we have a measurement device. It can only detect the particle within this range. When we click this button, a 1-second timer is activated. When the timer is up, the device makes a measurement and tells us if it detected the particle. It will say yes if the particle is anywhere within the measurement range.
Why don't they show us an actual experiment? Show us the actual measuring device. Why is it so difficult? What is wrong with these people? I mean, Making a video of an experiment is so cheap. Making these animations is so expensive. What's the point?
Now let's run a little experiment.
Let me check messages here. Okay, nothing interesting.
Experiment. The particle again starts at position 0 and has a velocity of 4 units per second.
Let's go back.
Now let's run a little experiment. The particle again starts at position 0 and has a velocity of 4 units per second. Our device has just been activated.
But it's never a particle. It's always a wave. It's just that the measurement, whatever the measuring device is, you don't measure a wave. You measure something. And that thing has a location. I don't know. They never tell us what the measuring process is. They never tell us. It's like it's always in some animation. It's always some abstract story. This is so ridiculous. How am I supposed to come up with a theory to? I need to come up with a theory to explain the animation. How is this going to work?
We'll make a measurement in 1 second. It's easy to see that by that time, the particle will be inside the measurement range. So we predict the device will say yes. This is the determinism of classical physics. If we know the initial state, we can predict the results of measurements. And now back to quantum physics. We paused just before the measurement. Can we now predict the result? The wave function doesn't tell us if the particle is inside the range or not. This is the famous indeterminism of quantum physics. But we can calculate probabilities. The volume of this slice is 35% of the total volume of this shape. And the remainder is outside. These are the probabilities of the 2 possible outcomes. This experiment ended with a yes result. If we run it again, we may end up with a no. The measurement also changes the wave. If the result is yes, the part outside the range gets zeroed out. Otherwise, the part inside the range is zeroed out. This is called wave function collapse.
Wait, what? Why is the wave is influenced by the measurement?
Otherwise, the part inside the range. This experiment ended with a yes result. If we run it again, we may end up with a no. The measurement also changes the wave. If the result is yes, the part outside the range gets zeroed out. Otherwise, the part inside the range is zeroed out. This is called wave function collapse.
I don't understand. I have no idea what you just said about the schmalapse.
Okay, repeat that. What to repeat
We'll
it
now
again?
run this
We can watch it again. It's a good video. I mean, it's really good. This is good stuff.
simulation in full before and after the measurement. We'll repeat it twice, once for each possible outcome, and then explain. The measurement made the wave function collapse. Afterwards, the function continues to evolve smoothly according to the Schrödinger equation. But since it's different now, it will evolve differently as well.
They're not explaining, like, what just happened? What is this evolution Schrodinger collapse. I don't know.
Here are 4 wave functions. They all give us the same information about the particle's position, but they rotate differently. This one rotates clockwise. This one rotates clockwise faster. This one counterclockwise. And the last one doesn't rotate at all. Let's see how they evolve with time. The rotations contain information about the particle's velocity, but it's not so easy to interpret. Here's how we make this information more readable. We'll use a mathematical operator called the Fourier transform. It decomposes the wave function into the frequencies that make it up, creating a new wave function. This new function gives us information about the particle's velocity, in the same way the original wave function gave us information about the particle's position. To be more accurate, it gives us information about momentum, but we'll explain about momentum only near the end of the video. For now, it will work fine as the velocity wave function. The peak of the wave is at 4 units, meaning the particle's most likely velocity is 4 units per second. But it's not the only velocity our particle can have. As before, we don't know its exact velocity, only the probability distribution. This explains the spreading phenomenon we saw before. We'll demonstrate this using an example from classical physics. Here's a cluster of 100 particles. We distributed them horizontally randomly according to the position wave function. We'll now assign them with random velocities according to the velocity wave function. So some of them are a little faster than 4 units per second, and some are a little slower. The center of the cluster moves at 4 units per second, and it is gradually spreading. But remember that our wave function represents just one particle, and that there's nothing quite like it in classical physics. The inverse operation of a Fourier transform is yet another Fourier transform, and we can in fact reconstruct the original wave function from the new one. So both functions contain all the information about the particle. We've already seen how adding curls to the position wave function changes velocity. It also works the other way around. Adding curls to the velocity wave function changes the particle's position.
What are these curls?
We'll now run our simulation again, this time showing both wave functions. When the position wave function collapses, the velocity wave function will snap as well, according to the Fourier transform.
I need to understand the derivation of what's the equation? Schrodinger's equation.
Derivation.
Yeah, do you know how to derive it?
No.
Let's see.
Sir, yes, sir. Do you think I'm cute, Private Powell? Do you think I'm funny? Sir, no, sir. Then wipe that disgusting grin off your face. Sir, yes, sir. Well, I need fucking time, sweetheart. Sir, I'm trying, sir. Private Powell, I'm going to give
Yeah,
you...
this is famous. I've seen this.
What?
This is famous. I've seen it. It's kind of funny. That it's from a movie.
It's an amazing movie.
Yeah.
This guy died. The drill sergeant died. He's an actual drill sergeant.
Oh.
So, yeah, they hired him as an advisor to teach the actor who was supposed to be the drill sergeant, but it was hopeless. It was just way too much to teach. So at the end, they just said, okay, why don't you take the part? So he's an actual drill sergeant. And he actually took the actors through the entire boot camp. You cannot fake what he did with them. You cannot fake it. He actually turned them into actual combat Marines. He took normal actors. You see the evolution of the actors. They became combat Marines. There's no way to fake it.
No, there's no way to fake that.
Yeah.
3 fucking seconds to wipe that stupid-looking grin off your face, or I will gouge out your eyeballs and skull fuck you. 1, 2, 3.
Sir, I can't help it.
Bullshit! Get on your knees, scumbag. Now choke yourself. God damn it, with my hand, numbnuts. Don't pull my fucking hand over there. I said choke yourself. Now lean forward and choke yourself.
Oh.
Are you through grinning?
Sir, yes, sir.
Bullshit, I can't hear you.
Sir, yes, sir.
Bullshit, I still can't hear you. Sounds off like you've got a pair.
Sir, yes, sir.
That's enough. Get on your feet. Private Pile, you had best square your ass away and start shitting me Tiffany cufflinks, or I will definitely fuck you up.
Sir, yes, sir. Sir, yes, sir.
Do you think I'm...
The woman that found Bin Laden said there will be a stairway.
What?
Damn, so much.
Yeah.
Why is there no AI model that can answer this really, really simple question? How many R's are in the word strawberry is stumping all of the major AI models right now.
Well, what's your blood type?
I'm an A.
How do you f*** a chicken Caesar? It's not a rhetorical question, Cupcake. Tell me.
Leave it alone.
I'm sorry, I can just take.
Guess the top 10 countries with the largest economy.
Don't fall for this at a dealership. It's an illegal sales tactic. Watch this. All right, sir, on that 2024 Mercedes C63 AMG.
This is Lyrebird. It is a unique bird of Australia. There are 2 types of it. One is superb lyrebird, and the other.
What?
Why are we seeing birds now?
So I don't fall asleep. Try not to fall asleep.
All 300 infantry. Toe jam.
Sir, yes, sir.
All 300 infantry. Adams.
Sir, yes, sir.
1,800 engineers. You go out and find mines. Cowboy.
Sir, yes, sir.
All 300 infantry. Taylor.
Sir, yes, sir.
All 300 infantry. Joker.
Sir, yes, sir.
4212 basic military journalism. You gotta be shitting me, Joker. You think you're Mickey Spillane? You think you're some kind of fucking writer?
Sir, I wrote for my high school newspaper, sir.
Jesus H. Christ, you're not a writer. You're a killer.
A killer, yes, sir.
Gomer Pyle. Gomer Pyle!
Sir, yes, sir.
You forget your fucking name? All 300 infantry. You made it. Pick it.
1, 2, 3, 1, 2, 3. Okay. More. Yeah.
This is it's too touching. I can't. This one I can't watch. That's too touching.
I'm gonna show you how to dress for your body type the right way. Number one, if you have a
once you get into armored fighting vehicles, space is at a premium.
Yeah.
Okay. So then we go to the grease gun. Very, very.
Why is there no AI model that can answer this really, really?
Hello?
Hi, guys. Are you having trouble getting in?
Yes, the code's not working.
Oh, shoot. Let me check on that for you.
She just emailed us at 8119, but that's not working to get in.
8119. Okay, hold on.
What's the reservation name?
Montana Lene.
And are you which one are you in Montana?
She's actually getting ready to get a rad too. She's actually getting ready to pull up too.
Oh, she ready to pull up?
Yes. She's getting ready to pull up with the rest of her stuff.
Okay, sorry about that. So for security purposes, I just need to verify Montana's ID in order to provide her access. Is she going to be here? Is she pulling up right now?
He's like 15, 20 minutes long.
Pick it.
Sir, yes, sir.
All 300 and
Bro, 1,000.
So you want to fly on an airplane and take your handgun with you? First thing you got to do is pick one of these up. This one.
Guess the top 10 countries with the.
I've heard of Ukraine, but.
What are we looking for?
What was this? What was it? No, I'm lost.
I agreed to be Stanley's technical advisor simply so I could get my foot in the door and audition for Stanley. I wanted to be Gunnery Sergeant Hartman, no question about it. I couldn't imagine anybody that could do it any better than I could. He looked me straight in the eyes and said, not a chance. I already have a contracted actor.
And it occurred to me, Lee Ermey, he used to dress in his drill instructor gear. And I thought, well, why don't we do it the way he used to do it? And I was videotaping it.
So, and I'm thinking Stanley Kubrick's got to see this. And then I had a little talk with these people and let them know that I might say a few unsavory things about their mothers and fathers.
Did your parents have any children that live? Sir, yes, sir. How about they regret that?
Then I went from one to the next, berating their family, what a dirtbag they look like, what's your name, scumbag.
Sir, Private Brown, sir!
Then I noticed Leon, he would tape them, then he would come to me. So I said, yep, it's working.
Eddie!
I agreed to be Stanley's technical advisor simply.
Planned. It was all planned. Oh my God. Did you get it?
Oh, I went to the bathroom.
Oh, so I just watched an interview with the drill sergeant. So he actually wanted to become an actor. He wanted that role. He agreed to be a technical advisor for Stanley Kubrick just in order to show them that he can be the actor.
Oh, that's amazing.
So he tricked Stanley Kubrick. That's Stanley Kubrick. Stanley Kubrick is probably the greatest producer. What do you call it? Director ever. One of the best ever.
So I could get my foot in the door and audition for Stanley. I wanted to be Gunnery Sergeant Hartman, no question about it. I couldn't imagine anybody that could do it.
Wait, we have a message? Okay. Let's continue. Okay, so what are we looking for?
I forgot.
No, I mean, we started to look for Einstein magnetism to explain magnetism as an artifact of electricity. So I guess we should do that. How special relativity makes magnets work. Watch this.
Only a few elements.
Oh, yeah.
Iron.
What?
We were doing that. That's right.
Yeah. Yeah.
Is one. Copper is not. But if you pass an electric current through any metal, it becomes a magnet, an electromagnet. But how does this work? Well, strangely enough, it's a consequence of special relativity.
Special relativity is the fact that in our universe, length and time aren't absolute. They're perceived differently by observers moving relative to each other, hence relativity. For example, if you measure carefully enough, you'll find that time passes slower for observers moving relative to you. Hey, Derek, when did you last shave?
6 hours ago.
Hey, watch this. Look at this.
For example, if you measure
Notice
carefully
what he
enough, you'll find
said.
that time passes slower for observers moving relative to you.
Is this true?
Time passes for what? What did he say?
Is this true? If the guy is falling, would you notice a difference in the clock rate if this guy is free falling and this guy is not?
Well, this I mean, an external observer would notice.
These guys are looking at each other. How do they observe each other's clocks? Like this clock is falling, and this clock is not falling. So the observer, looking at the faller clock, What is he going to see? A fast clock or a slow clock? All you need to know is that this guy, I mean, you don't need to know relativity. Relativity is just wave mechanics. All you need to know is that the reason he's falling is because the ether, he's falling with the ether, but not as fast as the ether. The ether is falling at 11,000 meters per second. He's falling much slower. Whereas this guy is experiencing the full 11,000 meters per second because this clock is not falling. So the ether relative to this clock is a little bit slower. So this clock is absolutely going to tick slower. This is right. The slowest clock will be the one that's falling at 11,000 meters per second.
No,
that's
but
the slowest.
in this stereo, don't they tick the same?
What?
Using this stereo, don't they tick the same?
I don't understand. Please
Don't it be
repeat.
the same in this theory?
Wait, my theory?
Yeah.
Ether? According to ether? Just think of the rubber duck. What do you mean? These are two rubber ducks, and there is water flowing at 11,000 meters per second going down. So this clock is moving at 11,000 meters per second upstream, and this one is a little bit less. So this clock is going to tick a little bit faster. Did I say slower? This clock is going to what? I can't understand what you're saying.
Slower.
No, I don't understand what you're saying.
You said slower.
Yeah, I meant faster. No, faster. So this one, the right one is faster.
If the ether is moving to the earth.
What? If the ether is moving, yeah, the ether is gravity. The ether waterfall. You can think of the ether as a waterfall. The ether waterfall is gravity. This is the reason why they're both being sucked towards the earth. So the guy on the right is moving a little bit slower relative to the ether. The guy on the left is moving a little bit faster relative to the ether. Therefore, the left clock will tick a little bit slower. Now, each one relative to each other. So since the one on the left is going to be ticking a little bit slower than the guy on the right, therefore, right, notice it has nothing to do with relative velocity. Anyway, so the guy on the left is observing the guy on the right. So the guy on the left, his clock, let's bring it up to maximum speed, to the speed of light. So let's say this is a black hole. So the clock on the left has stopped. So his brain, the guy on the left, his brain has stopped. And this clock has not stopped. So the guy on the left, his brain has slowed down. Therefore, he's going to see this clock ticking faster. Anyway, it's confusing. We still need to figure this out. We need to go through relativity. We need to see.
I mean, if it is vertical, like it will compensate. Because like it depends. Oh no. Okay, so which one is gonna go? Yeah, it's as you're saying. That clock that is with the ether is just going to go faster in general.
Right. This clock is ticking faster.
Yeah, it's as you said.
The question is, like when they say that they tested relativity, that's like when they say that they tested everything else. I don't trust them that they tested it. I don't think this scenario has ever been tested. They didn't test anything. They keep saying, "Oh, it's the most accurate theory in the history of the universe. We tested this. No, they didn't test anything. I don't believe it. I don't believe they tested anything. Einstein made predictions. And they didn't even test them. Like, what did they test? I mean, E equals mc squared, I guess. I don't know. I honestly, I don't, at this point, I don't know. I don't know.
Hey Derek, when did you last shave?
6 hours ago. Actually, it was 5 hours, 59 minutes, and 59.99999999996.
And moving objects are also contracted in their direction of motion.
You're looking slim, only in your frame of reference. So when an object is moving relative to you, it actually takes up less space than when it's not moving. And even though this effect is obviously way tinier than we've shown, length contraction is what makes an electromagnet work. Picture a copper wire. It consists of positive metal ions swimming in a sea of free negative electrons. Now the number of protons is equal to the number of negative electrons, so overall the wire is neutral. So if there were a positive charge or positively charged cat nearby, it would experience no force from the wire at all. And even if there were a current in the wire, the electrons would just be drifting in one direction, but the density of positive and negative charges would still be the same, and so the wire would be neutral, so no force on kitty. But what if the cat starts moving? Imagine for simplicity that the cat is moving.
Why do you need the cat to move?
Yeah, this doesn't make much sense.
Well, your audio is horrendous. Did you change anything about your audio? I have no idea what you're saying.
This doesn't make much, like, it doesn't explain anything. This, like, how does the magnet, how does one charge know where the other charge is?
But did you change your audio? It's like the echo is unbearable.
Really? No, why? That's
Yeah.
strange.
Now it's better. Now it's better. Now it's better.
I mean, I didn't do anything.
Now there's much less echo. I can understand what you're saying. Okay. No, but I don't understand. I mean, the cat doesn't need to move. When the electrons are moving, they should be contracting. You should have length contraction.
Yeah, but they always need a cat.
No, but why does the cat need to move?
Direction as the electrons with the same velocity. Well, now in my frame of reference, the wire is still neutral, and so there should be no force on the cat. But consider the same situation in her frame of reference.
In the cat's frame of reference, the positive charges in the wire are moving. So according to special relativity, their separation will be ever so slightly contracted. Also from this
Yeah, but that should have happened initially with the electrons.
perspective, the electrons aren't moving, so they'll be more spread out than before. Remember, objects take up more space when they're not moving than when they are. These two changes together mean there's a higher density of positive charges in the wire, so it's no longer neutral. It's positively charged, which means that the positively charged cat will...
When the cat was standing still, it should have felt the electrons are contracted because they were moving.
Feel a repulsive electric force from the wire.
But in my frame of reference, this seems mysterious. There's no force on a stationary charged cat, but
Why not? The electrons are moving, they should be contracted.
moving cat is somehow repelled from this neutral wire.
Why? Why only a moving cat? What's going on? What am I missing?
How do you account for that force? Well, we say it is the magnetic force. And that's mainly because a wire with current in it deflects nearby magnets. So really what this experiment shows is that a magnetic field is just an electric field viewed from a different frame of reference. In the cat's frame of reference, it is repelled from the wire due to the electric field created by the excess positive charges produced by the effects of length contraction. In my frame of reference, the cat is repelled from a neutral wire due to the magnetic field created by the current flowing in the wire. So whether you see it as an electric or a magnetic field just depends on your frame of reference, but in either case, the results are the same. So an electromagnet is an everyday example of special relativity in action. Now that might seem crazy since electrons drift through wires at about 0.00000000001% the speed of light. So how can special relativity have anything to do with it? Well, the truth is there are enough electrons in a wire and the electric interaction is so amazingly strong that even the minuscule effects of length contraction can produce.
So I think that is the secret of dark matter. Because there's so much quantum foam, so even the flow, let's say even at 10,000 meters per second, but there's so much that it might give us a multiple of the mass of the galaxy. So, but we need to go through the math.
Yeah, but I didn't get this part. Like, the electrons are moving very slow. Why do they have a relativistic effect?
Because of the number. There's just trillions and trillions and trillions.
Balances that produce a noticeable force.
So special relativity explains electromagnets, but what about permanent magnets?
Yeah, I mean, there can't be electrical currents flowing around inside lumps of rock, can there? Click here to go to Metaphysics, where we'll explore magnetite, compasses, and all the wizardry of permanent magnets.
So, but if we assume I mean, we said that our theory for now, let's assume.
It makes no sense. Like, this doesn't explain anything.
No. So I'm saying maybe an electron, what we experience, the magnetic moment of the electron, that's just a relativistic effect.
Yeah, but what about permanent magnets?
It's the same. That's what I'm saying. That's
Oh.
exactly what I'm saying. I'm coming to say
Okay.
that the electron's magnetic moment is just a relativistic effect of the of what?
Electron moving around? Of the
No.
spin of the electron?
Of the spin, yeah, of the spin, yeah.
Yeah,
The
okay.
spinning is creating a magnetic effect. It doesn't have a built-in magnetic effect. It has a built-in electric effect. Shut up.
Okay, so
Oh my
it
God.
spins and then there's length contraction in some direction. That's it.
No, I'm not even. Oh, yeah, it's a length contraction. Because it's spinning, there's a length contraction. The spinning creates a length contraction. I don't know. Something is creating a the magnetic effect is a relativistic effect. That's what Einstein said. The electron behaving like a
Why is
magnet.
it circular then?
What?
Like in a wire, why is it circular?
What is
Why does
circular?
it go around the wire?
What is going around the wire? What are you talking about?
Like the magnetic field is around the wire.
I don't understand what you're saying. What?
Magnetic field is around the wire.
Go. Oh.
So it should be perpendicular to the wire in that case. Why is it around?
Yeah, we can go watch videos about that. But that's what it's here, how magnetism really works.
Magnets can seem pretty mysterious. Their behavior is explained by Maxwell's equations. However, it's easy to convince yourself that Maxwell's equations prove that magnets don't work. That's the hook. If you're not careful, you can easily convince yourself that magnet theory is wrong. However, obviously magnets do work, so what's going on? And how does Einstein save the day? Let's dig into it.
La 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 la.
As you know, magnets are typically little chunks of metal that can pick up certain other metals. The details of how the magnets that hold children's art to the refrigerator.
How do magnets hold children to the fridge? When was this? Oh, it's 11 months ago. Oh my God, it's like yesterday.
Work can be kind of complicated, but luckily we can also make magnets using electricity. And the theory describing those magnets is much easier to work with. We call magnets made this way electromagnets, and they prove a weird and completely non-intuitive prediction of Einstein's theory of special relativity. Electricity and magnetism are related phenomena, but different. Electric force can be made by taking two electrically charged objects and bringing them near one another. Depending on the charges, the objects will either be attracted or repelled. Magnets are different. Magnetic forces are only felt between moving electric charges. If the charges are stationary, nothing happens. However, if one charge is moving and generates a magnetic force, a second moving charge will feel it. But that's the key point. For magnetism, both charges need to be moving. This effect can be seen most simply when we put two parallel wires near one another. If we run an electric current through the bottom one, it sets up a magnetic field around it. If we also run a current through the top wire in the same direction, it feels a force that pulls the wires together. If, instead, we run the current in the top wire in the opposite direction, the two wires are repelled. Now, I don't want to describe magnetism the way you might have learned in physics class. That's all very cool stuff, and you might have sprained your wrist doing all that right-hand rule jazz with this right-hand rule, or this one, or this one, but that's not the point of this video. If you've never took physics or you've forgotten all of it, I put links to some of the other videos on how magnetism and wires work in the description below. Mind you, I didn't make those videos, but some of you might welcome a refresher. On the other hand, you don't need to know all the math and whatnot. What you need to know is that moving charges are needed to make a magnetic force, and that if the motion is the same in the same direction, they'll attract. If they're in opposite direction, they'll repel. Now, it turns out that if I were to try to explain the problem using wires, it gets super complicated very fast and highly mathematical. So let's use a simplified example that tells you what's going on. And in the end, I'll tell you about where to find a more detailed explanation. So, okay, instead of two parallel wires, let's have one wire that is carrying a current and a single positive charge moving either in the direction of the current or against it. If the wire has no current, but the charge is moving, there's no magnetic force. If the wire has a current and the charge isn't moving, there's no magnetic force. However, if there's a current and a moving charge, there's a magnetic force, and it's the same basic idea as wires. Same direction attract, opposite direction repel. Everything I just told you is right, and I've taught it dozens of times in introductory physics classes. However, now let's think like Einstein. I mean, sure, you can say that the charge is moving, but from the charge's point of view, it's not moving. It's stationary, and the world is moving. Since we need a moving charge to feel a magnetic force, this means that the charge should feel no magnetic force, at least in its own reference frame.
So that makes absolutely no sense at all. We, in our frame, think the charge should feel force, but the charge in its frame thinks it shouldn't. And that, as they say, is a paradox. Relativity does weird things, but two observers should agree if the charge moves toward or away from the wire. So that's how you can convince yourself that magnet theory is wrong. Yet smart people believe in magnet theory. So how's it saved? Well, to do that, we need to think about what's really going on in the wire. In the wire, there are positive and negative charges. The wire itself is electrically neutral, but in standard electricity theory, we say that the positive charges are moving and the negative ones are stationary. Yes, there are issues with that. I'll get back to that. But let's stick with the traditional ideas. So an outside observer will see stationary negative charges and moving positive ones in the wire, and the moving charge above the wire. For illustration purposes, we'll say they're moving to the right. The positive ones set up a magnetic field, and there we are. If we ask what the positive charge on the top sees in the reference frame in which it's stationary, the negative charges are moving to the left. The positive charges are probably still moving to the right, but slower than they appear to someone who's stationary compared to the wire. And this is where relativity comes in and the magic happens. Remember that special relativity says that not only do moving observers have clocks that tick more slowly, it's also true that moving objects get shorter. This is called length contraction. I made a video about that, which you can watch. The link is in the description. Thus, according to the charge outside the wire, it sees the negative charge in the wire moving fast and the positive ones moving slower. Because the negative charges in the wire are moving faster, according to the outside charge, the spacing between the negative charges is contracted more than the positive ones. I'll even stop the animation so you can see the effect. This means that the negative charges are more concentrated than positive ones, and that means that the wire now has a net negative electric charge. Since we know that opposites attract, what happens is that while the now stationary top charge doesn't feel a magnetic force downward, it feels an electric force downward. What once was magnetism is now electricity, but either way, the force is downward. What happens if we look at the case where the charge outside the wire is moving in the direction opposite the current, at least from our point of view? Well, we do the same thing. Since we see the negative charges in the wire to be stationary and the positive ones to be moving, in the frame of the charge outside the wire, it sees the positive charges in the wire moving faster than the negative ones. This means that the charge outside the wire sees more concentrated positive charge than negative. Since the top charge is positive and same sign electric charges repel, the charge outside the wire feels a repulsive force and is pushed away from the wire. Again, the outside observer and the charge outside the wire disagree on magnetism and electricity, but they both agree that the charge is pushed away from the wire. So let's recap. Moving charges make and feel magnetic forces. If charges aren't moving, they neither make nor feel magnetic forces. And depending on the reference frame, the charges could be either moving or not. Luckily, special relativity saves the day and converts magnetism into electricity and vice versa. Okay, so this is all very cool. What about the caveats? Well, to begin with, this is all very hand-wavy. If you want to see how it's done with math and equations and whatnot, it was first written down in a book by Edward Purcell back in the 1960s. The book was revised and released back in 2013, and the references in the description. Plus, there are some online resources.
So this is from the 60s. So Einstein came up with it in 1905. So Einstein, I don't think Einstein never figured this out. So it comes out of Einstein.
Okay, but wait a minute. So if you have current in the same direction at the same speed,
we'll go watch. I'm gonna go watch
and there
more
will be no
videos.
magnetism. Is that
No, he's saying there's no difference between magnetism and electricity. It's
yeah?
the
But but listen to what I'm asking. I'm asking if you have current in two wires and they're going in the same direction at the same, and the current is going at the same speed, there will be no forces. Like that's a prediction that should be tested.
Two currents, same direction.
That is just that. Two currents, same direction, same speed.
No, either way, there is going to be either repulsion or attraction.
Okay, but according to this theory, there should not be any force.
So,
But I think there is.
Here, I mean, let's assume positive. So if they're both positive moving in the same direction, they both.
They
I
both see the negative charges being contracted.
But,
I see.
But
Okay.
my wire is contracted just as much as yours. So there should be the zero net effect.
But it's not about the wire. They see the negative.
I don't know. Well, let's go watch more videos. Well,
Okay,
I
that
don't
makes
want to.
sense. No, I'm beginning to understand how this works.
Just to go through the argument more simply. Some of you will also note that we know in a real wire that it's the negative electrons that are moving, not the imaginary positive ones. Yep, that's true. But it really doesn't change anything. If you think it through, you get the same result. The absolutely key point here is that the experiment I have described here absolutely proves that Einstein's length contraction is a real phenomenon. Magnets wouldn't work otherwise. And another thing is that
It doesn't
the wire,
prove
the
it.
electrons-
That's circular reasoning.
No,
It's like that's circular
but
reasoning. Like you come from the presupposition that it works, and then you conclude that it works.
Well,
So,
no. I mean,
that's
it's
circular
fine.
reasoning.
absolutely proves that Einstein's length contraction is a real phenomenon. Magnets wouldn't work otherwise.
No, and this has nothing to do with magnets. This is about
No. So I think he's
The key
saying
point
that
here is that the experiment I have described here absolutely proves that Einstein's length contraction is a real phenomenon. Magnets wouldn't work otherwise.
this is a normal magnet. So he thinks even a normal magnet.
Yeah, but how
not
does a
just
normal magnet do that?
So I think
This is not explaining much of anything in the end of the day.
Fine,
Like,
fine. We'll go watch more stuff.
Otherwise. And another thing is amazing. In the wire, the electrons are moving much less than a millimeter per second. While most relativistic effects need you to be moving at a substantial fraction of the speed of light, for magnetism, the speeds are tiny, and yet relativity theory really matters. This is some really weird stuff, but it's true. Magnetism proves Einstein's theory of relativity and the crazy sounding idea of Lorentz contraction. And now you know something you didn't know this morning. You're welcome. Okay, like I said, this is a crazy thing, but it's absolutely true, even if it's a bit mind-blowing. If you like getting your mind blown, I sure hope you'll like and subscribe and share. And I hope you'll return for future videos where we'll visit other physics topics. And when you watch those topics, I hope you'll agree with me that physics, especially the mind-blowing stuff, is everything.
Didn't he say he's going to give us links to other videos? Look, US Department of Energy, Fermi Lab. Let's see this.
Okay, so it literally doesn't explain what
In a recent video, I described how electromagnets work.
Magnets don't have that.
We'll see.
With a focus on the length contraction predicted by special relativity. That topic is one of my very favorites because it demonstrates relativistic length contraction of velocities under a centimeter per second. But many of you asked for an explanation not of electromagnets, but permanent ones. And that's a very interesting question. Let's dig into it. The question of how permanent magnets work is certainly interesting. Magnets most definitely seem like magic. It turns out that a lot of things have to line up just so to make a permanent magnet. The relevant phenomena involves fundamental particle physics, atomic physics, and small scale physics, sizes in the ballpark of a fraction of a millimeter. It's all very complicated, but hopefully I can make it clear. So first, the basics. Magnets have two poles, a north and south. You can't have one without the other. Like poles repel and opposite poles attract. And two magnets pointing in the opposite direction cancel each other out, leaving no magnet at all. Magnets are made of atoms, and therefore the origins of magnetism must come from the atoms or the constituents of atoms and how they move. The relevant bits of atoms are electrons and protons, both of which have electric charge and both of which can move. Moving charges generate magnetic fields. I made a video about that. It was a way cool video, by the way. So let's see if the moving charges of the atom play a role. Protons are about 2,000 times heavier than electrons, which means that they're harder to move. So the motion of protons is basically irrelevant. Well, what about electrons? Their motion is much greater. And if an electron orbited an atom like a planet orbits a star, that circular motion would make a magnet. The electrons don't move that way. Instead, they're found inside clouds surrounding the atomic nucleus. They move in all directions. And the net effect is that the motion of the electrons doesn't generate significant magnetic field. What about the protons and electrons themselves? Back in 1922, in what is now called the Stern-Gerlach experiment, researchers proved that each electron is a tiny magnet all by itself. A decade later, a team led by Otto Stern showed that protons are magnets too. So maybe that's what makes a magnet? It turns out that the strength of a proton magnet is about 700 times less than an electron magnet, so we can ignore the protons entirely, at least from a magnet point of view. That leaves the electron. Are electrons what cause a magnet to be a magnet? Well, yes, but it's more complicated than that. To begin with, what causes an electron to be a magnet? The short answer is, well, nobody knows. It's like other questions. Why does an electron have a wave and a particle nature? Why does it have an electric charge? Why does it have a mass it does? Why does it act like a tiny magnet? Why do people put ketchup on hot dogs? All of those are questions with no good answers. They're just facts.
People put ketchup on hot dogs. Wow.
For which we have no good explanation. I don't know, maybe Freud figured out the whole ketchup thing. But for the rest, like the strength of the magnet for a single electron, this is just the way the universe is. Figuring out why, we'll have to wait for some future discovery. So is the intrinsic magnetic strength of electrons the cause of permanent magnets? Well, yes. But why but? It's because there's more to the story. Let's move to the next chapter of the story. According to the Schrodinger equation and confirming measurements, of course, atoms have a series of recurring configurations called energy levels. Each energy level can accept a different number of electrons, 2, 6, 10, 14, etc. These energy level configurations explain why the periodic table of elements is the shape it does. Now, just why all that is true will take several videos to explain, and we don't have time to do that here. For now, just accept that it's true. There's another restriction from quantum mechanics that is relevant here, and that's how the electrons are allowed to enter each energy level. For half of the electrons in an energy level, the magnetic electrons can be oriented in one direction, but once you hit the halfway mark, the rest of the electrons have to be in the opposite direction. This is simply because of the laws of quantum mechanics and how particles with a spin of the electron congregate together. So let's see the consequences of that. I'll use one of the energy levels that contain 10 electrons as an example. Remember that in order for an atom to be magnetic, the electrons in the atom have to be in the same direction. Otherwise, one electron cancels the other. If we put one electron in the energy level, the atom has the magnetic properties of one electron. If we put two electrons in, the atom acts like a magnet twice as strong as a single electron. 3 electrons, triple the magnetism, 4, 4, and 5, 5. But add a 6th electron, and that's past the halfway point. So that electron has to enter as a magnet oriented opposite the others. So this atom will only have the magnetic properties of 4 electrons. 7 electrons.
What is he talking about? I don't know what he's talking. Do you know anything of what he's talking about?
He's talking about electrons in atoms in the material.
What is
And their orientation.
What is this 6 halfway point? It's past the halfway point? What is he talking about? What halfway point?
Oh,
He said something about the sixth electron, that's past the halfway point, and this electron has to
3 electrons, triple the magnetism, 4, 4, and 5, 5.
Oh, it's
That's 6
like the levels in the atom.
the what?
The levels, the energy levels in the atom.
What's an energy level?
The orbitals. I think he's talking about that, but you can rewind a little bit.
Rewind? He didn't say anything.
Yeah, rewind the video. Okay, probably fine.
A series of recurring configurations called energy levels. Each energy level can accept a different number of electrons, 2, 6, 10, 14, etc. These energy level configurations explain why the periodic table.
What's an energy level?
You know, electrons have like orbitals, and each orbital has energy levels, or not?
Not really.
Okay, but yeah, I probably should see that first then. It's about the structure of the electron, of the atom.
Welcome to my vlog. Okay. So listen up. Okay, so here's the thing. Fashion Week is coming up. And we're gonna be talking
You
about
gave up?
today.
No. Well,
Just wanted to see some boobs then.
Oh yeah, definitely. That's all I wanted to see. No, I'm curious about the title. The dark side of plus. I love plus modeling. I mean, some plus models are pretty, but a lot of them are not. I mean, she has a good face. I actually once dated a plus model. Gorgeous.
Hope a lot of my girlies are walking and
Okay, so what are we looking for?
What we're looking for is explaining electron orbitals or atom orbitals.
In a previous video, we learnt that the nucleus is at the center of an atom, and that it is made up of protons and neutrons. And around this central point, we find the electrons. We also know that in a neutral atom, the number of electrons always equals the number of protons. So in a neutral atom of carbon, there are 6 protons, which mean there must be 6 electrons. The electrons in the atom are organized around the nucleus in different energy levels or shells. Shells can only hold a certain amount of electrons. The first and innermost shell can only hold a maximum of 2 electrons. The shells which come after this can hold a maximum of 8 electrons. Let's look at some arrangements. Lithium has 3 protons. Therefore, it has 3 electrons. The first 2 electrons are placed in the first shell, closest to the nucleus, and the third electron is placed in the second shell. 2 plus 1, 3 electrons. These diagrams are called dot and cross diagrams, and they're used to show the electronic configuration of an element. You need to be able to draw these diagrams, as well as being able to write the electronic configuration in a written form. For lithium, this will be written as Li2,1. In the diagram, the nucleus is represented by the element symbol or a central black dot. The energy levels are represented by circles around the nucleus, and the electrons are represented by dots or crosses. Let's look at some more examples. Carbon has 6 protons, therefore it has 6 electrons. The first 2 electrons are placed in the first shell, and the next 4 are placed in the second shell. 2 plus 4, 6 electrons. This would be written as C2,4. Magnesium has 12 protons, therefore it has 12 electrons. The first 2 are placed in the first shell, the next 8 are placed in the second shell, and the last 2 are placed in the third shell. 2 plus 8 plus 2, 12 electrons. This would be written as Mg282. The organization of these energy levels is what gives elements their different reactivities. The number of electrons in the outer shell of an atom tells you the group number to which they belong on the periodic table.
But she didn't explain what an energy level is.
Yeah, but you know, you already know
Members
it
of the
goes
same
like
group
that.
with the same number of electrons in the outer shell have similar reactivities. So electrons are arranged in shells or energy levels around the nucleus. Each energy level has a maximum number of electrons it can hold. The lowest energy level is always filled first and can only hold 2 electrons, while the levels after this can hold a maximum of 8 electrons. The number of electrons in the outer shell of an atom determines which group the element belongs to on the periodic table, and elements in the same group have similar reactivities.
No idea. I mean, I knew all of this from before.
To other properties. Particle. The fact that the electron is a fundamental particle. The fact that an electron is a fundamental particle means that an electron is not a collection of smaller particles. In other words, an electron is just what you measure. An electron has measurable properties such as its mass, electric charge, and magnetic dipole moment. On the other hand, electrons are negatively charged, which means they are attracted by a positive charge. So we can liken the nucleus of an atom to a valve into which electrons can fall. The atomic nucleus is a potential valve, meaning that an electron near it can fall into it if it doesn't have enough kinetic energy. We can liken this system to a planetary system. Therefore, one would expect electrons to orbit the nucleus in the same way that planets orbit stars. But there's a problem. An orbit is a state of constant acceleration, and an accelerating electron will radiate energy according to the theory of electromagnetism. And the electron emitting energy will spiral towards the nucleus. One of the reasons why the theory of quantum mechanics was developed was to explain the background of the spiraling electron emitting energy. Therefore, to go beyond this situation is to enter the field of quantum mechanics. In quantum mechanics, the matter is described by a wave function, which is one of the fundamental properties of matter. This means that all matter behaves like a wave and can interfere with itself. This interference excludes most of the electron orbits and is characterized by a series of orbits of increasing energy, but there are only certain discrete energy values in the orbit. Therefore, an electron bound to a nucleus can only exist in certain allowed energy states. These energy states are related to other properties, such as angular momentum. An electron can make discrete quantum jumps between energy levels by absorbing or emitting energy in the form of photons of light. Since the energy levels are discrete, the photon energies absorbed or emitted will also be discrete. So one might ask, why the electrons don't radiate all their energy and collapse to the bottom of the valve, to the nucleus? This is because there is a minimum allowed energy state. There are no more energy states below this minimum energy state. This minimum energy state is centered in the nucleus, but it extends beyond the nucleus. It is not an orbit, it is the lowest possible energy state, and it has no angular momentum. Therefore, it cannot be seen as an orbit in any sense. Rather, we can say that the electron has a cloud of probabilities centered on the nucleus. But because the mass of the electron is very light, it spreads out beyond the nucleus. The reason why the electron is in such a diffuse state is the Heisenberg uncertainty principle. On the other hand, the electron...
This is nonsense. She's not saying anything.
Yeah, unfortunately.
Hey, crazies, you've probably seen atomic orbitals before. They're those weird-looking shapes that show up near the end of a chemistry class. The problem is, they're always so static. The universe isn't static, it's dynamic. It's all about change. Atomic orbitals are no exception. Let me show you the way they were meant to be seen. This episode was made possible by generous supporters on Patreon. Our first obstacle is going to be that we can't actually see any of this, at least not directly. The super tiny wavelengths of visible light are thousands of times larger than an atom. Optical images just aren't possible at that scale. The best we can do is a diagram based on electron microscope data. Every one of these spherical lumps is a gold atom. That makes atoms look like tangible little...
Yeah, light is like huge. It's 0.65 micrometer. Like red light is 0.65. So basically 1 micrometer. A micrometer is huge. Like a millimeter is huge. You can easily, obviously, see a millimeter. You can fit probably like almost. You should be able to see a 1/100th of a millimeter. So that is 10 micrometers. That's basically the wavelength of red light.
Yeah, it's amazing. Yeah, I never thought about that.
It's almost the same order of magnitude. So, so you shouldn't be able to see an atom using light. It's just way too big. Light waves are huge, and like, what is the physical size of a photon? Like how many wavelets, how many waves? Like what are the actual dimensions of a photon?
Yeah, good question. I have no idea. Like they should be visible if they were that big. You should be able to see them in a microscope or something very easily. That's strange.
Like a single photon, the way I envision it, it's like a wavelet. It's like a container. It's like a water droplet. I would imagine it's basically like a water droplet. And it should be the size of a water droplet, maybe much bigger, because it's moving so fast. It could be even much bigger. Anyway, inside it, I would expect to find a few wavefronts. It has to be a few wavefronts because I thought about this. Otherwise, you cannot get an interference pattern from a single photon. If you want a single photon to interfere with itself, then it has to have multiple wavefronts. So, like an electron, if we assume the double slit experiment is correct, then a single electron should include a few wavefronts in it. Maybe even a lot. Maybe even, I don't know what number. It could be huge. Also, an electron could be huge. Like a moving electron could be huge. And when the moving electron,
yeah, electron seems to vary in size as well. Like in the atom, it seems to be bigger.
No, in the atom, it's tiny.
No, in the atom, no. Like for it depends. I don't know. It's strange. It's hard to conceptualize.
What's amazing is that when you look with a normal microscope, you're able to see Brownian motion. Did you ever see Brownian motion?
You can see Brownian motion in what conditions? Like you can put some like pollens and stuff.
Yeah.
Then you
like,
can see it. Yeah.
Have you seen it?
No, I've never seen it.
You have to see this. This is gonna change your life.
Probably not, but we can see it.
Russia seems to be losing the war with Ukraine.
I mean, it depends on who you ask.
Whose side are you?
Then they're winning amazingly. Yeah. Like, who knows?
Oh, here is a better explanation.
Hmm?
Recently, someone left me this comment on one of my videos. The link was to an old video by Veritasium, in which he explains how relativity makes electromagnets work. It was a good video, but it skipped over a couple of things that needed an explanation. Watching it, I could understand why some people may have been left puzzled. I don't usually make reaction videos, but I thought, what the hell? In his video, Veritasium introduces the Lorentz contraction, which tells us how moving objects contract in the direction of motion. He then goes on to explain how this contraction makes electromagnets work. I will play the relevant parts of the video and then come back with my comments.
A copper wire. It consists of positive metal ions swimming in a sea of free negative electrons. Now, the number of protons is equal to the number of negative electrons, so overall the wire is neutral. So if there were a positive charge or positively charged cat nearby, it would experience no force from the wire at all. And even if there were a current in the wire, the electrons would just be drifting in one direction, but the density of positive and negative charges would still be the same, and so the wire would be neutral, so no force on the kitty. But what if the cat starts moving?
I don't understand why you need the cat to move. Why isn't the cat observing the electrons?
Yeah, I don't understand that either. It's so strange.
What do you call contracted? Yeah.
Imagine for simplicity that the cat is moving in the same direction as the electrons with the same velocity. Well, now in my frame of reference, the wire is still neutral, and so there should be no force on the cat. But consider the same situation in her frame of reference.
In the cat's frame of reference, the positive charges in the wire are moving.
What changed? Now she's gonna feel the positives because they're contracted, but before she couldn't feel the electrons that must have been contracted.
So according to special relativity, their separation will be ever so slightly contracted. Also, from this perspective, the electrons aren't moving, so they'll be more spread out than before. Remember, objects take up more space when they're not moving than when they are.
It would be more spread out than before, so you agree they were contracted?
These two changes together mean there's a higher density of positive charges in the wire, so it's no longer neutral. It's positively charged, which means that the positively charged cat will feel a repulsive electric force from the wire.
But in my frame of reference, this seems mysterious. There's no force on a stationary charged cat, but a moving cat is somehow repelled from this neutral wire. How do you account for that force? Well, we say it is the magnetic force. And that's mainly because a wire with current in it deflects nearby magnets. So really what this experiment shows is that a magnetic field is just an electric field viewed from a different frame of reference. In the cat's frame of reference, it is repelled from the wire due to the electric field created by the excess positive charges produced by the effects of length contraction. In my frame of reference, the cat is repelled from a neutral wire due to the magnetic field created.
Yeah, you're thinking about the magnetic field curling around, but that's the magnetic field curling around. A charge doesn't know that it's curled. A charge moving through the field goes into, oh, it should start rotating if it's a uniform field, but it's not uniform. So the charge should move down because of right-hand rule. But because of relativity, I mean, it makes sense.
Created by the current flowing in the wire. So whether you see it as an electric or a magnetic field just depends on your frame of reference, but in either case, the results are the same. So an electromagnet is an everyday example of special relativity in action.
All right, so he says that if the electrons were moving, stationary cat would not experience any force because the wire is still neutral. But the question one might ask is, if the electrons are moving, shouldn't they experience a Lorentz contraction? And wouldn't this create an overall negative charge, which would then attract a positively charged cat? The answer to the first question is yes, and the answer to the second question is no. The space between the electrons in the direction of motion does indeed contract, leading to a higher density of electrons. But now the electrons feel each other's electric charge and want to push away from each other. And since the electrons are essentially free to move around inside the wire, they drift apart until they reach an electrically neutral configuration. That is, until their density matches the density of the positive charges. So indeed, the density of moving electrons would not change. But you might be asking, if in a...
What?
No, the density does not change.
He says that they move faster, they get contracted, but then they feel repulsion.
No,
so
they don't
move
feel
up.
repulsion. Okay,
That's what he said.
Rewind. I think he said that they don't feel repulsion.
You know, he says they do. They feel repulsion. That's why they move apart until they are neutral.
But now the electrons feel each other's electric charge and want to push away from each other. And since the electrons are essentially free to move around inside the wire, they drift apart until they reach an electrically neutral configuration. That is, until their density matches the density of the positive charges. So indeed, the density of moving electrons would not change. But you might be asking, if in a stationary frame, the moving electrons adjust their positions to counter the net negative electric charge, should they not do the same in a moving frame to counter the net positive electric charge? Well, no. The additional positive electric charge, because it is uniformly distributed, positive charges. So indeed, the density of moving electrons would not change. But you might be asking, if in a stationary frame, the moving electrons adjust their positions to counter the net negative electric charge, should they not do the same in a moving frame to counter the net positive electric charge? Well, no. The additional positive electric charge, because it is uniformly distributed along the direction of motion, exerts a force on each electron in all directions, which amounts to a zero net force. And since the positive charges are bound to the material, they themselves cannot adjust their positions to counter the Lorentz contraction. The last thing that might puzzle some people is, why does the moving observer measure the distance between electrons to be larger than what the state...
He's asking good questions. He said, but if the protons are moving together, then the electrons should want to neutralize it, and they should move in closer as well.
Because it is uniformly distributed along the direction of motion, exerts a force on each electron in all directions, which amounts to a zero net force. And since the...
I don't understand that. I mean, I don't know. I mean, this is just an explanation. Who says the explanation is correct?
Yeah. That's my question.
In this video, I'm going to show you a mind-blowing example of the connection between the electric and magnetic forces. You're going to see exactly why magnetic fields are generated by moving charges. Let's quickly go over the basic facts. Naturally occurring magnetic materials were known to the ancient Greeks, and by the 12th century, the Chinese were navigating using compasses made out of magnetic lodestone. From a modern perspective, we would say that the compass needle was aligning with the Earth's magnetic field. The magnetic field is an abstract way of thinking about the force that a magnet exerts on other magnetic materials or on charged particles. The motion of the interior of the Earth generates a magnetic field, and this magnetic field protects us from harmful radiation in space. The sun emits a number of charged particles, for example, electrons and protons, and these are deflected by the Earth's magnetic field, away from causing harm in the lower atmosphere. The magnetic field produces a force on moving charges. A stationary charged particle will not feel a force from the Earth's magnetic field. We can see this from the mathematical expression of the force. The force is equal to the charge of the particle, Q, times its velocity, times the strength of the magnetic field, B. So you can see that the larger the velocity, the larger the magnetic force. And if the velocity was zero, then, well, the magnetic force would be zero, because the force is proportional to the velocity, and therefore a stationary charged particle experiences no force from the magnetic field. In contrast, the electric field acts on any charged particle, whether they're moving or not. Our experiences with the electric force began even before we knew about magnetism. Ancient peoples knew that rubbing an amber rod with cat's fur would cause it to attract other objects around it. We now know that the process of rubbing the amber rod with the cat's fur is transferring electrons from the cat's fur onto the amber rod. And so the amber rod gains an excess of electrons, and since electrons are negatively charged, the amber rod as a whole becomes negatively charged. The cat would become positively charged. And again, we've invented this abstract idea of the electric field to help us describe the forces that a negatively charged or positively charged object exerts on the charged particles surrounding it. Because this amber rod is now negatively charged, it's going to attract positively charged particles. So a proton that's just sitting in empty space is going to be attracted towards the rod. Even if the proton were moving, its motion would be bent towards the rod. An electron would feel a force away from the rod, and so its motion would be bent away from the rod. And again, we have a simple expression for the force produced by an electric field. The strength of the force of the electric field is equal to the charge of the particle multiplied by the magnitude of the electric field. But until the 19th century, we didn't know that there was a connection between these two forces. Sure, they both acted on charged particles, but electricity was produced by the action of rubbing two objects together, and magnetic materials were dug out of the ground. It was a man named Hans Christian Ørsted who provided the first evidence that the electric and magnetic forces were connected. And he was performing experiments on electric currents. In order to produce an electric current, you create an electric field in the wire, and you usually do this using a battery. And this electric field causes the charged particles in the wire to move. In the case of a metallic wire like copper, the positively charged particles are the nucleuses of the different copper atoms, and these form a lattice inside the wire, a rigid lattice, so these particles can't move in response to the electric field. They're fixed in place. But the electrons that surround these nuclei are free to move, and so the electric field is able to move these electrons, and the movement of the electrons is called an electric current. And it's the same electric current that delivers power to your household appliances. And Ørsted discovered that if he held his compass next to the wire, the needle of the compass was deflected when there was an electric current flowing. So the electric field in the wire produces a current, and the current, in turn, produces a magnetic field outside the wire. And because it's a magnetic field, that means it's going to interact with any moving charged particles near the wire. So if a proton is moving parallel to the wire, in this case it's going to be deflected towards the wire. And if an electron is moving parallel to the wire, well, it's going to be deflected away from the wire. And this really was a huge discovery that led to a flurry of results that explored this connection between the electric field and the magnetic field. And this research eventually culminated in Maxwell's equations of electromagnetism.
By the way, did you know you can polarize, you can change light polarization using a magnet?
Yeah, probably. That makes perfect sense.
It's called Faraday's effect. I looked into it. Okay.
And Maxwell's equations give you a formula for how the magnetic field changes in response to an electric field, and how an electric field changes in response to a magnetic field. But it doesn't tell you why they do it. The actual mechanics behind the relationship between the electric and magnetic fields is incredibly surprising and at the same time very beautiful. Maxwell's equations were the inspiration for Einstein to produce the theory of special relativity, and actually it's special relativity that hides the secret, that is the connection between the electric and magnetic fields. For those of you that know special relativity, this could come as a big shock, because special relativity is a theory about objects that are moving very fast, and in our case, nothing appears to be moving very fast. We have a current in the wire, but the electrons moving through the wire under the influence of the electric field are actually moving very, very slowly. And even the charged particles passing by the wire are moving at mundane, everyday speeds. Nothing is traveling anywhere near 10% of the speed of light, which is really the threshold where we need to start using special relativity. But by the end of this video, we're going to derive an equation that describes the magnetic force on a charged particle moving near a wire using only the formulae of electrostatics. That's the electric field produced by static charges, and special relativity. And given that we can find our answer using special relativity, what's the first thing we're going to do? Well, we're going to transform ourselves into the frame of reference of the particle which is experiencing the force. That means that we're going to start moving so that we're alongside those particles moving outside the wire, and we're going to try and see what's happening from their perspective. So once we start moving at the speed v, which is the speed our proton and electron are moving at, well, they're going to be stationary. And the positive ions in the wire, well, they were stationary before, but now we've started moving at the speed v. They're going to be coming towards us at that same speed. So it appears like all the ions in the wire are going to be rushing towards us at this speed v. And what about the electrons? Well, they were moving at the speed v0 towards us originally, but now that we've started moving at speed v as well, then surely the speed they're coming towards us is just v plus v0. But actually, this is where it gets a bit tricky, because special relativity takes us outside the realm of our everyday understanding of time and space and velocity. And special relativity tells us that the velocities of objects don't add in the simple way that we think they do. For example, if the particles on the outside of the wire were moving at some crazy velocity, like 3/4 the speed of light, and the particles inside the wire were also moving at 3/4 the speed of light, then when we add those two velocities together, we get something that is 1.5 times the speed of light. But the whole premise of special relativity is that nothing can travel faster than the speed of light. So it necessitates that adding velocities doesn't happen in the usual way. And instead, if we want to add two velocities...
Not a premise. It's not a premise. We know the premises of relativity. It's the laws of physics are constant and the speed of light is constant. Those are the two premises. There's no premise other than that.
In our case, v and v0 together. We need to scale the resultant velocity. It's easier if I just show you the formula. The actual velocity that will be produced is v plus v0 divided by 1 plus v times v0 over c squared, where c is the speed of light. Ordinarily, when v and v0 are very much smaller than c, then the number in the denominator, 1 plus v0 over c squared, is going to be very, very, very close to 1. And so the velocities will appear to add in the normal way. We'll have some answer that's very, very close to v plus v0. There are some other weird properties that special relativity introduces. So what are these other weird properties? Well, the first is that the force due to the electric field experienced by our charged particles is different depending on whether we're moving alongside the particle. That means we're in the reference frame where the particle is stationary, or whether we're watching the particle move by us. That's the frame of reference where the positive ions in the wire are stationary. And the ratio of those two forces is given by something called the Lorentz factor. And the Lorentz factor is a very important parameter in special relativity. Things like space and time, when we start to move very fast, are squashed and stretched by this factor gamma.
And so it is in the case of the force provided by the electric field. If we measure the force as we're moving alongside the particle, and then stop and stand still and watch the particle whiz by, and then measure the force that we've measured the second time is going to be a factor of 1 over gamma times the force we measured when we were moving alongside that particle. And I've already mentioned the other strange fact that we need, and that is that once we start moving, the distance between objects gets squashed, space gets squashed, and space gets squashed again by the factor of 1 over gamma. So that means that suppose my table has a length d0 when I'm sat in front of it. As soon as I start to move past it, the length of that table is going to shorten a little, and the length that I'll measure as I'm moving past it, which we'll call d, is going to be equal to the original length, d0, divided by the Lorentz factor, gamma. And since the Lorentz factor is always going to be greater than 1, then the new length we measure is actually shorter than the length we measure when we're sat next to the desk. And this discussion applies equally well to the particles in our wire. So supposing the positive ions are a distance apart d0 when we're sat next to the wire, when we start moving at the speed v alongside the charged particles, we're going to be moving past those positive ions. So the distance between them is going to appear smaller than it was before. And it's going to be smaller by the factor 1 divided by gamma. And the same is true of the electrons. But the electrons are moving at speed u, and u is faster than the speed v. So the electrons are going to be squashed together even more. And the distance between them, instead of being d0, is going to be d0 over gamma of u. Oh, or is it? Because actually, if you think about it, when we were sitting next to the wire, the electrons were already moving. And so because of that motion, they were already closer together than they would be if they were stationary. To find out how close they would be together if they were stationary, we need to multiply by gamma instead of dividing by gamma. So that means when stationary, the electrons would be d0 times gamma of v0 part. And that's the number that we need to divide by gamma of u to find the distance between them when we're moving along at speed v outside the wire. So can you see that because the distance between the electrons is now less than the distance between the positive ions, then there's an overabundance of electric charge in the wire. There's more electrons in the length of wire than there are positive ions in that same length of wire. And so we have a situation exactly like we had with the amber rod. Our length of wire has more electrons than it has positive ions. And so when we're moving alongside it at this speed v, it appears negatively charged. And we know that a negatively charged object has an electric field, and the electric field lines point in towards the center of that object. And so if I were a proton moving alongside this wire, I would be attracted towards it because the wire is negative. And if I were an electron moving alongside the wire, I'd be repelled away from it. Since we're also moving at the same speed as this electron and proton, they're just going to move towards and away from the wire. But if we're sitting in our stationary frame and we see these particles go past, we're going to see them either bend towards or away from the wire. And we're going to say that they've experienced a force due to the magnetic field produced in the wire. But if we were to move alongside those charged particles, alongside the electron, alongside the proton, we'd actually see the wires not having a magnetic field, but having an electric field, because the wire would appear negatively charged to us. So here is the really deep connection between the electric and the magnetic fields. The particle that appears to be influenced by a magnetic field is actually just experiencing an electric field. Isn't that great? What a beautiful connection between the electric and the magnetic fields. And who'd have thought that it would be special relativity that holds the answer? Now, some of you might not take my word for it. And so we're actually going to derive the force on these charged particles. It's going to involve a page or so of equations though, so don't worry if you don't feel like you can follow along with it. You already have the physical insight behind this connection. Now, from the perspective of an observer, stationary with respect to the wire, he would say that the wire has produced a magnetic field. And so the force on those charged particles moving past the wire is going to be equal to Q times V times B. And what's the strength of the magnetic field produced by the current in the wire? The strength of the magnetic field is equal to mu0, which is just a constant, so you don't really need to worry about it, times by the current in the wire, I, divided by 2 pi times r, where r is the distance away from the wire that the charged particle is. So that's the ordinary way of thinking about this problem. But we now know this extraordinary way of thinking about it. From the perspective of the moving charges, the wire itself is negatively charged. But exactly how much is it negatively charged? Well, to find that out, we need to know exactly how much more densely packed the electrons are than the positive ions. First, let's see if we can simplify gamma of u. Well, we know it's a horrible mess. It's equal to 1 divided by the square root of 1 minus v plus v0 divided by 1 plus v0 over c squared, all squared. And then that whole...
Oh my god. Oh my god. Okay, but
what is the difference between an electric field and a magnetic field? An electric field is caused by both moving and non-moving electric charges. A magnetic field, on the other hand, is generated only by moving charges. A positive charge is the source of the electric field, and negative charge is the sink of the electric field. In nature, negative and positive charges can occur independently of each other, as electric monopoles. Magnetic monopoles, on the other hand, as far as we know, do not exist in nature. That means there is no magnetic north pole or magnetic south pole that occurs alone. North pole as a source and south pole as a sink always occur together. Magnetic field lines are closed loops. Electric field lines, on the other hand, do not have to be closed, but can, for example, go to infinity, like the field lines of a point charge. A charge Q in an electric field E experiences an electric force equal to Q times E. A moving charge in a magnetic field B, perpendicular to the motion, experiences a magnetic force equal to Q times V times B. The unit of the electric field is volt per meter, and the unit of the magnetic field is volt-second per square meter, or in short, Tesla. When an electric charge is placed in an external electric field, the charge is accelerated. As a result, the charge changes its kinetic energy. On the other hand, when an electric charge is placed in a magnetic field, the charge is not accelerated. The charge does not change its energy. In short, an electric field does work on the charge, but a magnetic field does not. The magnetic field does no work on the charge even when the charge is moving. An electric field can be shielded, for example with the help of a Faraday cage. A magnetic field, on the other hand, cannot be shielded, but at least deflected.
Okay, let's go for that again and let's see how this works with the interpretation that they're the same. Well, let's go through that again.
that?
There was some
What is the
problem.
difference between an electric
I'm gonna kill myself. No, he didn't say he. What's the
No, but let's just go through this. Okay.
field and a magnetic field? An electric field is caused by both moving and non-moving electric charges. A magnetic field...
1 second, I have a message.
You can go. We can go after this. I think we're both kind of tired.
Wait, what? You want to go?
No, let's just see this and then we go. I think we
Okay.
both have.
I mean, I'm somewhat lacking motivation, but hold on. Let me. Amber is asking me a question. Okay. All right. Okay. You want to watch this? Okay.
Field, on the other hand, is generated only by moving charges. A positive charge is the source of the electric field.
The main thing that he said that's interesting is that a charge, that a magnetic field doesn't do any work on a charge. So a charge needs to be moving in order for a magnetic field to have any impact on it, because a magnetic field is not going to linearly accelerate a charge. It's only going to cause it to go into like a rotation. So it has to be moving.
Negative charge is the sink of the electric field. In nature, negative and positive charges can occur independently of each other as electric monopoles. Magnetic monopoles, on the other hand, as far as we know, do not exist in nature. That means there is no magnetic north pole or magnetic south pole that occurs alone. North pole as a source and south pole as a...
The fact that there is no magnetic monopole, that indicates to me, that's like a hint that it's not intrinsic. That the electron doesn't have an
That it has to
what?
depend on movement or something like that.
Yeah, that it's a relativistic effect. Now I don't believe in relativity, so we'll have to explain it using the ether, but it should work.
It's
I
probably
mean,
something spinning in the ether.
what? Wait, what?
Like something spinning in the ether.
I mean,
What it
we
does.
know that if you move through the ether, you get time dilated. And if two people move through the ether at different rates, they have relativistic effects because they each one's clock relative to the ether is different. So they're different relative to each other. So relativity still holds. All the calculus of relativity still holds. That's the beauty of the way I view the universe. I don't have to rethink relativity. I can take whatever they say about relativity and I can just assume it's correct. If they did, it's just that Einstein's relativity is much more complicated than ether relativity. Ether relativity is much more straightforward because it's just relative to the medium. It's just more straightforward. It's just wave mechanics. But it should give you the same results. So, but the fact that there is no monopole, that to me, that's like a little bit of it. I never thought about this. I mean, I've heard about this issue that they never discovered a monopole, a
Have you
magnetic.
ever seen like a ferromagnetic cell?
A ferromagnetic cell? What do you mean cell?
Yeah, I will show
I don't
you.
know.
It's really cool
Oh my
because it
God.
polarizes light and creates interference pathways.
But you promised we're finishing up and we're gonna go kill ourselves. You promised.
Okay, I can leave you to watch
I
it.
definitely heard you making that promise. I
Yeah.
guarantee it. Wait, how long have we've been here for 3 hours?
Jeez, we've been here for 3 hours already.
Look, what we're trying to do is really hard. I mean, but if we were trying to sit now and do like an online course or like a university course, it would be just as difficult. Maybe, yeah, those are really difficult. I mean, it doesn't matter what course, whatever course you do, it's so difficult. What we're doing, that's legitimate research. We're thinking about everything outside of the box, and we're doing everything like from first principles. So what we're doing is really hard. We're not just taking a course. We're taking many online courses simultaneously in order to really resolve issues.
It's not even a course because there's like we don't have any ground truth.
Yes, exactly.
Like, it's a lot more difficult.
And the ground truth that we have derived.
Yeah, I'll put it on Discord so you can like
Okay.
watch it when you want.
Okay, let me see one second.
This one is good. This one has like a good image. If it has that image, then it's great. Yeah, it has
Nature's
that image.
secret of magnetism.
Hello, everybody. I was able to create a even more powerful or sensitive
You
supercell.
can just skip to the image.
What?
You can just skip to the image. It's
Okay.
like on what
The
that is.
reason why I actually have this, it's something that's this lets me
What
actually
is he showing?
goes over here.
What is that?
And literally, I could rebuild this thing too, including my book.
What is that? What is
surprised.
that?
Now look
Oh,
at this. If I
that.
get it on
Oh, right. Like if you shine light on a.
He derived
It's
this.
like this is like there's a magnet below that in the center.
But what is the source of light? Are these just LEDs?
Yeah, it's just LEDs, and then you have
I don't know. I don't know what an LED is. Forget it. It's too complicated. I need to know what an LED is. I don't see the
I
point.
mean, an LED is just light. It's just monochromatic light.
I don't know what an LED. I need to look into what an LED is, and I don't know what the magnetic effect is. What the magnet? What kind of effect it's having?
It's polarizing the light. Yeah, it's polarizing the LEDs.
Also, too, the spatial field.
How is this relevant to our discussion about spin, the nature of spin?
Well, I think that will alter the spin.
Oh, you mean because it's the photons? It's causing a change of spin in the photons?
Yeah, I think that's essentially what.
So this
the
is
spin of the
this is
photons
just.
aligning with the magnetic field.
So you're saying this is just a Faraday's effect?
Yeah, I think it could be, but I mean, I can't be sure. That's the problem. Like, I can see it's.
I
like
don't
a-
know. I don't. It's too difficult. I don't know. I don't know. It's too difficult.
it
It's
is
good to know. Look, there's so many experiments. We need to know. I need to go through every experiment in the history of humanity and understand each one. And I think when finally AI becomes like we have, I don't know, 3-4 generations from now, they'll be able to figure these things out because they'll just take every online course. They'll go through every experiment and they'll just be able to tell you, okay, it has to be this and
Yeah,
done.
they just need to teach AI how to reason. I don't know why they don't do that. It's
No,
very
you don't need. No, they don't need to teach it how. You don't need to teach it how to reason.
No,
It
you
knows.
need- No,
No.
it doesn't. That's the problem right now. It doesn't know how to
So
reason.
it takes a course on. It takes reason course. There's many YouTube videos about reason. An AI
Yes,
will learn.
that's why it's easy to do. But they're not doing it.
No, they feed it Wikipedia. Wikipedia is full of reason. There's many entries in Wikipedia. What is reason?
Yeah, but it's not learning how to reason. It's learning how to
Yes.
reproduce reason.
That's good enough. That's what
No,
you do.
it's not learning how to criticize. Like if it has.
You don't know it. You don't know how to. No, you don't. You don't know how to criticize. You are imitating people who have criticized. You're just an imitator.
No, I understand logic. It's not imitation.
No, you don't know. No, you don't. There's no such. Look, this is my. You're walking into my line of research.
You also.
You don't know.
Into my.
You
field, which is
no. You don't know anything. Everything you know, you don't know. You think you know. Like everything you do, you're just imitating. You're just imitating with with fluctuations of random fluctuations, and that's ideas. Your ideas you're having, these are just fluctuations.
I know how neurons work. That's all.
You don't know how neurons work.
Yes,
you
I
don't.
do. How
No.
do I know how neurons work? I literally had a course on producing neural networks.
No, you don't.
Of course I do.
Anyway, not really. Maybe a little bit. Anyway.
Okay.
Look, okay, let's. We've been here for 3 hours.
Yes, we
I
can
know
do it.
we need to continue this. This is really difficult. We're stepping into, I mean, literally spin. I mean, it's like with every passing day, the challenge keeps growing. It's like particle wave duality at this point is such a joke compared to Bell's theorem, which is now also a joke. But now spin, maybe in a few days we'll look back and what?
You know what this Tinty says about spin is that there is spin because the electron is actually two particles. Which is
Whatever. I don't know. Right now, I'm thinking maybe the spin is just it is physically spinning, or whatever it is. It's a relativistic effect. It's doing something to the ether. Maybe it has.
That's definitely what's going on. And the
So the
magnet-
mass.
And
So
the
the
magnet
mass.
is just like a disturbance in the ether. I'll send you another video to watch.
So what I'm thinking is, because ever since I saw the lecture, Kathy loves physics and history, so she gave a lecture about Faraday, how he never understood math, but he understood fields. He actually came up with the notion of fields that Maxwell developed into his field equations. But Maxwell took Faraday's drawings with all these cables and pipes. So the notion of a field, that's actually from Faraday. So Faraday said that the universe is basically a fluid, and the electric attraction, that's the motion of a fluid. So I'm thinking maybe maybe there is some sort of an ether flow, even though I believe ether flow is gravity, but there might be some sort of an ether flow. I don't know. It's so difficult because ether flow is gravity. So I cannot use ether flow for electric attraction because then also
Maybe you can. Like, if you look at this video on 9 minutes, you'll see a way.
Okay, let's continue tomorrow.
Yeah,
Let's
okay.
continue, 'cause today
I
I'm.
already sent the video, so it's fine. We can continue.
Yeah. Okay, I'll talk to you tomorrow. I'll DM you when I'm ready. All right,
See you.
man. Thank you so much. See you tomorrow. Bye.
Thank you, dude.
All right, bye.